Hello, my dear students. I hope you all are really doing great. Student, first of all, I welcome you all on this amazing platform of PhysicsWallah English channel. Students, in this ongoing champion series, now we have moved to lecture number 16. And if I talk about today's class, the topic which we are going to discuss today is taken from class 12 physical chemistry, one of the most important topic for all the competitive exam, whether it is JEE mains, NEET or advanced. And the name of this particular topic is solid state. Highly important topic taken from class 12th physical chemistry. So students, without wasting any further time, let's start our discussion on solid state. So students, if I talk about today's class, let's start with classification of states of matter. Student, if we talk about the classification of the different states of matter for our competitive exam, from examination point of view, we have to study only three states of matter, that is solid state, liquid state and the gaseous state. Although one more state of matter is there, and that's nothing but the plasma state, but we are not going to discuss about this plasma state, right? It's not there in our syllabus. So students, already this gaseous state we have discussed, right? Now it's time to discuss about solid state of matter. So students, now throughout this lecture, we'll be discussing about one state of matter, and that is solid state. Let's move ahead. Students, now let's start our discussion on solid state. And student, let's first of all discuss the properties of solid. If I talk about the properties of solid, the first property is, in case of solid state, the intermolecular force of attraction between the molecule is very high. And if the intermolecular force of attraction is high, in that case, what will happen? The molecular motion, the randomness of the molecule will be less. And if the randomness of the molecule is less, can I say it will have a definite volume and a definite shape. And the reason is high intermolecular force of attraction. The next one, already we have discussed this. In case of solid, the molecular force of attraction or the intermolecular force of attraction is very high. And if intermolecular force of attraction is high, in that case, can I say even the molecular motion will also be very less. Am I clear, student? So they don't show the property of diffusion and diffusion. Next one, least molecular motion. Once again, the reason is very high intermolecular force of attraction. And students, here the constituent particles, that is atoms, ions or the molecules present in the solids, are closely packed. And the reason is, once again, very high intermolecular force of attraction, right? One more thing we can conclude from here. If they are closely packed because of the high intermolecular force of attraction, in that case, can I say the compressibility will be very less. So solids are least compressible. Let's write this point also. Least compressible. Right, student? I hope you understood all these properties. So let's move ahead. Students, now let's discuss about the classification of solids based on the arrangement of constituent particle, that is constituent atoms, ions or molecules. So classification of solids on the basis of arrangement. On the basis of arrangement. Now, on the basis of arrangement of constituent particles, solids are divided in two categories: crystalline solids and the next one is amorphous solids. Students, I hope and I believe you are already familiar with these two terms. The first one, crystalline solid, and the second one, amorphous solid. Can you define these two types? Yeah. Crystalline solids. If I talk about crystalline solids, here the constituent particles are arranged in a definite order, right? The substance whose constituent particles are arranged in a definite geometric pattern in a three-dimensional space is referred as crystalline solids. So in case of crystalline solids, all the constituent particles, whether it is atom, ions or molecules, are arranged in a definite order. Whereas if I talk about amorphous solid, here the constituent particles are not arranged in a definite order. They are arranged in a random order. Am I clear, students? In the three-dimensional space. So not a definite pattern. Not a definite pattern or order of arrangement of constituent particle in case of amorphous solids, and in case of crystalline solids there is a fixed and definite arrangement of constituent particles. I hope you understood this term crystalline solid and amorphous solid. Now let's discuss briefly about the difference between these two solids. Okay, students, if I talk about the difference between the crystalline solids and amorphous solids, these are the properties on the basis of which we can differentiate between a crystalline solid and a amorphous solid. Student, if I talk about this property shape, crystalline solids have a fixed geometrical shape, right? They are having a definite characteristic geometrical shape, right? Why it's so? The reason is because here the constituent particles are arranged in a definite order. If I talk about this amorphous solids, they are having a irregular shape, and the reason is here the constituent particle atoms or ions are arranged in a irregular order, not in a definite order. Am I clear? Next one, nature. Students, crystalline solids are referred as true solids, whereas amorphous solids are referred as pseudo solids or supercooled liquids. This is really important. Crystalline solids are the only true solids, whereas the amorphous solids are pseudo solids or supercooled liquids. Next one, arrangement of particles. Crystalline solids are long range order. What do we mean by this term long range order? Basically, students, in case of crystalline solids, this definite arrangement of particle or constituent atoms is up to a very large distance. Up to a very large distance or throughout the lattice, throughout the structure, we have a definite arrangement, right? Whereas in case of amorphous solids, they are referred as short range order. Why? Because in case of amorphous solids, the constituent particles are arranged in a definite order, but up to a certain distance only, up to few row only, right? Let's try to understand it like this. In a class, the first three benches, the arrangement of students, they sit properly, right? But from fourth row onwards, from fifth row onwards, there is not a definite pattern, there is not a definite order. So in case of amorphous solids, the arrangement of particle is short range. They are arranged in a definite order, but up to a certain distance only, up to a short range distance only. Am I clear? Next one, an isotropy. This property is really important. Now let's discuss a very important terminology, and that is an isotropy. Let's first of all define it. Isotropy, the properties which are same in all direction. Iso, same, tropy, direction. So there are certain physical property which are same in all directions. Students, amorphous solids are referred as isotropic solids. They are isotropic in nature. Means their certain physical properties are same in all directions. Whether it's electrical conductivity, refractive index, viscosity, all these properties are same in all directions. Whereas Crystalline solids are anisotropic in nature. What do we mean by this term anisotropic? Students, there are certain physical properties which are not same in all directions, and these properties are electrical conductivity. They are direction dependent property. In a certain direction, I may have the magnitude x. In the other direction, I will have the magnitude y. So these properties have not the same value in all directions. So in case of crystalline solids, or we say crystalline solids are anisotropic in nature, whereas amorphous solids are isotropic in nature. Am I clear? Next one, melting point. Student, if I talk about crystalline solids, they have a fixed melting points. Let's suppose I'm having a crystalline solid, suppose rock salt, NaCl. So for this NaCl, there will be a fixed melting point. Am I clear? Whereas if I talk about amorphous solids, they don't have fixed melting point. And what's the reason behind it? Because in case of amorphous solids, the bond energy between the two constituent atoms is not same throughout the structure, right? So basically what happens, as we provide heat, amorphous solid gradually soften over a range of temperature and then they start melting. Am I clear? You might have seen the melting of rubber, the melting of plastic. First, it gradually softens and then it starts flowing. And the reason is the bond energy between the two constituent particles is not same throughout the structure in case of amorphous solids, where it is same in case of crystalline solids. Next one, the Cleavers property. Student, when we cut a crystalline solid with sharp edge tool, they simply split into two pieces and the newly generated surfaces are plain and smooth. Whenever we cut a crystalline solid, first they cut into two equal pieces, right? And then the newly generated piece will, or the face of the newly generated piece will be plain and smooth. Whereas if I cut a amorphous solid with a sharp edge tool, they cut into pieces with irregular surface. Whenever you will cut plastic, right, the surface or the newly formed piece will not have a plain surface. They will have a irregular surface. Am I clear? Next one, heat of fusion. In case of crystalline solids, the heat of fusion is fixed because the bond energy of each and every constituent particle is same, where it's not same in case of amorphous solid. And if it's not same, every bond will need different amount of energy, right? So heat of fusion will be different in case of amorphous solid, where it will be same, it will be constant in case of crystalline solids. Crystalline solids have a definite characteristics, heat of fusion. They have a fixed heat of fusion. Am I clear? Let's move ahead. So students, these are few examples of crystalline solids or true solids. Sulfur, right? We have studied the different allotropic forms also, rhombic form, monoclinic form. Diamond, perfect example of crystalline solids, right? Quartz, rock salt, NaCl, this is nothing but rock salt. It's also a crystalline solids, or we say it as a true solid. Let's move ahead. If I talk about amorphous solids, or these amorphous solids are referred as pseudo solids or supercooled liquids. Supercooled liquids. The examples are rubber, plastic, quartz glass, rubber, plastic, pitch. These are the examples of amorphous solids. Let's move ahead, student. Classify the following as amorphous solids or crystalline solids. Student, we can easily classify, right? I hope you can easily do it. And the answers are also given. Once you classify, please match it with the answers given here. Am I clear? Let's move ahead. Students, on the basis of intermolecular force of attraction operating between the constituent particles, crystalline solids are divided into 4 different categories. The first one, molecular solid. Second one, ionic solid. Third one, network solid. And the fourth one is metallic solid. Student, if I talk about this molecular crystalline solid, it's further class divided into three different categories: non-polar molecular solid, polar molecular solid, and H-bonded molecular solid. We'll discuss one by one. If I talk about this molecular crystalline solid, student, here the constituent particles are held together by physical force of attraction or van der Waals force of attraction. So here constituent particles are physically bonded, and the force of attraction which is responsible for this physical bond is van der Waals force of attraction. Now, depending on the nature of or the type of the constituent particles, we may have polar molecular solid. If the constituent particles are polar, we may have non-polar molecular solids if the constituent atoms or particles are non-polar, and we have H-bonded molecular solid, right? We'll discuss about this also. Student, non-polar molecular solid. If I talk about this, here the constituent particles are non-polar, and if the constituent particles are non-polar, in that case the physical force of attraction which is operating is London force or dispersion force, right? London force, right? Can you tell me one example? Yeah, iodine solid, CO2 solid, all these are non-polar molecules. Argon solid, so all these are non-polar molecules, and in case of non-polar molecules or non-polar molecular solids, the force which is operating is London force. Am I clear? Next one, polar molecular solids. Van der Waals force of attraction. Now here the molecules are polar, right? They are having a certain dipole moment. So here the physical force of attraction which is operating is dipole. And can you tell me one example of this polar molecular solid? HCl. It's polar in nature, right? HCl in the solid form, it's a polar molecular solid. If I talk about hydrogen bonded molecular solid, here's also first the constituent atoms or molecules are polar, and second, so basically it's a case of dipole, and now this hydrogen bonding is a special case of dipole interaction, and the best example of this H bonded molecular solid is ice, H2O solid. Am I clear? Okay. Next one, ionic crystalline solids. Which type of molecular force of attraction will be operating here? Intermolecular force of attraction, which is operating is Coulombic force. Coulombic force operating between the constituent ions, cations and anions, oppositively charged particles. Coulombic force of attraction will be operating here. Here the molecules are bonded together by ionic bond or electrovalent bond. Am I clear? The next one, network crystalline solids. Here the constituent particles or atoms or molecules are chemically bonded, and they are bonded by covalent force of attraction. Covalently bonded in case of network crystalline solid, right? The best example is diamond. It's a network crystalline solid. Graphite, network crystalline solid. And the last one, metallic crystalline solids. Here the force of attraction which is operating is metallic bonding between metals and metal. Which type of bonding will be there? Metallic bonding. Am I clear, students? Metallic bonding. Now let's discuss a bit detail about all these crystalline solids. First, molecular solid. Already discussed the types of force or the attractive force which is operating is physical force or van der Waals force. If the molecule is polar, in that case dipole. If the molecule is non-polar, in that case London force. In case of non-polar molecule like CCl4, H2, I2, CO2, right? Obviously, if the molecule are physically bonded, it will be a soft one, right? about the other types of molecular solid, that is polar, and in case of polar molecular solids, the physical force of attraction which is operating is dipole-dipole. Example is HCl or SO2 solids, right? Once again, here also the force of attraction is physical force, so the molecules will be held together by a weak force of attraction. It will be soft in nature, will have low melting point. Am I clear? And it will be also a insulator, because here the constituent particles are not ions. Am I clear? Next one, hydrogen bonded molecule. The next type of molecular solid is hydrogen bonded molecule. The best example is ice, H2O solid, right? Here now, among all the physical force of attraction, hydrogen bonding is the strongest one, right? So if the physical force of attraction is strong, now the molecule is going to be a hard. The physical nature is going to be a physical appearance. It will be a hard one. Am I clear? Once again, it's also an insulator. And if I talk about the melting point will be relatively higher as compared to non-polar solids, right? Because here the force of attraction is relatively high. Moving to the next type of solids which we have to study is ionic solids. The constituent particles are the constituent particles are ions, cations and anions, and the force of attraction operating between these ions are Coulombic force. Am I clear? Or electrostatic force of attraction. Example, NaCl, all the ionic solids, NaCl, MgO, ZnS, CaF2, Na2O, all these things, right? Students, whenever we have ionic bond, the physical appearance, it will be hard but brittle, right? Okay. If I talk about the conductivity of the ionic solids, students, if not in molten state, then they won't conduct electricity, because in the solid state, the constituent ions will be held together by strong electrostatic force of attraction. So there won't be movement of free electrons. There won't be movement of ions, right? And if the ions, electrons will not move, they won't conduct electricity. But in molten state, they will conduct electricity, or in aqueous state, they will split into ions and then they will start conducting. Am I clear? If I talk about melting point, since the intermolecular force of attraction is very high, they will have high melting point. Am I clear? Next one, metallic solids. Student, if I talk about metallic solids, here the constituent particles are positively ions immersed in a sea of delocalized electrons. We'll study about this in metallic bonding in chemical bonding chapter. Am I clear? Okay. If I talk about the examples, it is iron solid, copper solid, Ag solids. These are the examples of metallic solids. Hard but malleable. All the properties of metals, they are hard but malleable and ductile. Student, now metallic solids conduct electricity, right? Because of this delocalized electrons. Am I clear? If I talk about the melting point, once again, the intermolecular force of attraction is high, so melting point is going to be high. Okay. Next one, covalent solids or network solids. Here the constituent particles are atoms. The intermolecular force of attraction which is operating here is chemical covalent bond, covalent bonding. Example, SiO2, quartz, diamond, graphite, all these are example of network solids, right? If I talk about the conductivity, they don't conduct. Melting point relatively very high. Am I clear, students? So I hope you understood all these different types of crystalline solids, and these crystalline solids were classified on the basis of the intermolecular force of attraction operating. Am I clear? Let's move ahead. Students, now let's start our discussion on crystalline solids. And here, first of all, let's define some important terms and parameters which are required to study about this crystalline solids. And these important terms are, first one, space lattice or crystal lattice. How do we define it? Student, it can be simply defined as a regular, infinitely long three-dimensional arrangement of particles in space, right? Long, regular, up to infinite distance, a definite arrangement of constituent particle in three-dimensional space is referred as crystal lattice, or we say it as space lattice. Am I clear, students? The next important term, lattice point. Student, basically in this crystal lattice, each and every constituent particles is represented by a point which is referred as these constituent particles, these particles, they are referred as lattice points. Lattice points. Am I clear? Each particle in a lattice is depicted by a point. This one, each and every constituent particle will be represented by a point, and this point in the space lattice is referred as lattice point. Next one, each point in a crystal lattice represents one constituent particles, which may be an atom, molecule, or ion. Am I clear? These constituent particles may be atom, molecule, or ion. Students, now let's define one more important term, and this is nothing but unit cell. How do we define it? Can you define unit cell? Student, we define unit cell for this crystalline solid. Unit cell is basically the smallest portion of the crystalline lattice, which when repeated in three dimensions generates the entire lattice. Am I clear? It's the smallest portion of a crystal lattice, which when repeated in three dimensions generates the entire lattice. Student, here you can easily say lot of n number of cubical blocks, right? And now these cubical blocks are basically arranged in a three-dimensional space, right? Up to a very large distance. Now if I take about one of these cubical blocks, this one of the cubical block will be referred as your unit cell. Basically this entire lattice is the repetition of these cubical unit cells, right, along three dimensions. Am I clear? So unit cell is the smallest portion of a crystal lattice, which when repeated in three dimensions generates the entire lattice. Okay, let's move ahead. Student, if I talk about this classification of unit cell, basically they are classified in two categories: primitive unit cell or centered unit cell. Primitive unit cell and centered unit cell. Student, if I talk about this primitive unit cell, here the constituent particles are present only at the corners. The constituent particles, which is represented by a point. So these points you will find only at the corners. Only at corners. Whereas if I talk about the centered unit cell, here the constituent particles are present at corner as well as center also, right? If I talk about the different types of centered unit cell, we have body centered unit cell, we have face centered unit cell, and we have end centered unit cell. We'll talk about all these centered unit cell one by one. Okay, let's move ahead. Student, if I talk about this primitive unit cell, it's here the constituent particle, which is represented by a point, which is represented by a sphere, will be present only at the corners. The constituent particles are present only at corners of this cube, right? It is referred as primitive unit cell, or we also say it as simple cubic unit cell, SCC lattice. We'll study about this, don't worry. Primitive unit cell. In case of primitive unit cell, the constituent particles are present only at the corners. Okay. Students, now to define a unit cell, basically we need few parameters, and these parameters are basically the edge length and the angle between the faces. So basically there are two parameters required to define a unit cell, and these parameters are crystallographic axis, basically you may say it as edge length, and the second one, crystallographic angles, you may say it as interfacial angle, angle between the faces, angle between faces, right? Basically, the interfacial angle is represented by the symbol alpha, beta and gamma, whereas the edge length is represented by the symbol ABC, length, width and height. Am I clear? Okay, so students, on the basis of these two parameters, we have a total of 7 crystalline lattice, and these 7 crystalline lattice are referred as Bravais lattice. Am I clear? On the basis of the lattice parameter A, B, C, alpha, beta, gamma, we have 7 crystalline systems, and these 7 crystalline systems are known as Bravais lattice. We'll discuss about these 7 Bravais lattice one by one. Okay. Students, these are the 7 Bravais lattice. Let's discuss the parameters of these 7 Bravais lattice. Student, if I talk about the edge length, in case of cubical Bravais lattice, in case of cubical lattice, the edge length is same. A equals to B equals to C. Length, width, height equal. Even the interfacial angles are also equal. Alpha equals to beta equals to gamma, that's equals to 90 degree. Student, if I talk about the unit cell which we find in cubical type of lattice is primitive unit cell, that is simple unit cell. Here the constituent particles are present only at the corners, body centered unit cell and face centered unit cell. So in cubical type of lattice, we have 3 types of unit cell. 3 types of unit cell. Right? Okay. The next one, CT, tetragonal. Student, here 2 edge length are same. A equals to B, not equals to C. Start cutting. As we move from C to T to O, C to O, start cutting this equality sign. So now A equals to B, not equals to C. Student, if I talk about the interfacial angle, still the interfacial angle is same. Alpha equals to beta equals to gamma, and that equals to 90 degree. If I talk about the type of unit cell which we find here, primitive and body centered. So 2 types of unit cell from here. 2 types from tetragonal. Am I clear? So CT, if I talk about the angles, alpha, beta, gamma equals to 90. If I talk about the edge length, in case of C, it's A equals to B equals to C. In case of T, A equals to B, not equals to C. Next one, O, orthorhombic, or we say it as rhombic. CTO, CTO of a company, Chief Technical Officer, right? Now, here, start cutting this equality sign. So I have cut this one. Here in case of O, I am going to cut the second one also. So now here A not equals to B, not equals to C. Alpha equals to beta equals to gamma, still equals to 90 degree. So in case of CTO, the interfacial angle alpha equals to beta equals to gamma equals to 90 degree. This one you can remember easily, right? If I talk about the different types of unit cell which we find in such type of lattice system, the first one is primitive, body centered, face centered and end centered. So this type of crystalline lattice system, or this type of lattice system which is orthorhombic, contains maximum number of unit cell, 4 unit cell, 4 types of unit cell, all primitive and centered unit cell we find in case of orthorhombic or rhombic. Next one, MT, management training, right? Here students, once again A not equals to B, not equals to C. In case of M also, and in case of T also, A not equals to B, not equals to C. So CTO, A equals to B equals to C. T, A equals to B, not equals to C. O, A not equals to B, not equals to C. M, A not equals to B, not equals to C. T, management trainee, A not equals to B, not equals to C in both M as well as T. Now interfacial angle, alpha equals to gamma equals to 90 degree, beta not equals to 90 degree. Whereas in case of T, Trainee, triclinic, monoclinic and triclinic. Monoclinic, alpha equals to gamma equals to 90 degree, beta not equals to 90 degree, whereas in case of triclinic, alpha not equals to beta not equals to gamma not equals to 90 degree. If I talk about the type of unit cell, in case of monoclinic, two types of unit cell, primitive and end-centered. Whereas in case of triclinic, we have only one type of unit cell, and that is primitive. Right, students? So 3, 2, 5, 4, 9, 12 unit cell till yet. Next one. Rhombohedral or trigonal. A equals to B equals to C. Rhombohedral. A equals to B equals to C. If I talk about the angle, alpha equals to beta equals to gamma not equals to 90 degree. Just like a case of rhombus. Right? Okay. Now here, simply you have to consider one thing. Angles are not same, but the edge length are same in case of rhombohedral. Am I clear? Or we say it as trigonal. If I talk about the type of unit cell which is found here, it's primitive only. Primitive is found almost everywhere. Primitive 1. Am I clear? If I talk about the next one, hexagonal. Hexagonal, students, we know it. A equals to B not equals to the height. Right? Length and width are same. Height is not the same. Am I clear? If I talk about the interfacial angle, two angles are same. Alpha and beta, they are 90 degree, and gamma, that's 120 degree. Alpha equals to beta equals to 90, gamma equals to 120 degree. So you can remember it like this HR. In H, A equals to B not equals to C. In case of rhombohedral, A equals to B equals to C. So HR recruits management trainee, and this management trainee gets promoted to CTO. Am I clear? So this technique, through this mnemonic CTO, MT, HR, you can remember this table, and this table is really, really important. Student, let's move ahead. So these are the different types of Bravais lattice: cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, triclinic. One unit cell here, one unit cell here. In case of rhombohedral also, we have one unit cell or two unit cell. Rhombohedral, we have one unit cell. In case of monoclinic, two unit cell, two unit cell here, one and one rhombohedral. In case of this one, cubical unit cell, we have three types of unit cell. Here. In case of tetragonal, we have two types of unit cell, right? Two types of unit cell here, students. In orthorhombic, we have four types of unit cell. In case of hexagonal, we have one type of unit cell. So it's 3 plus 2, 5 plus 4, 9, 10, 10, 2, 12, 1, 13, 1, 14. So if I talk about the different types of unit cell which are found in these crystalline solids, 14. Am I clear, students? Let's move ahead. Students, now we have one more important term which we have to understand, and that's there on your screen. It's nothing but coordination number. How do we define it? Student, it can be simply defined as the number of nearest neighbor of a particular atom, right? The number of particles surrounding a test particle. Suppose this is my test particle, and now I have to find out the coordination number of this particle. This is my test particle. So now I will see how many particles are surrounding this particle. The number of particles surrounding my test particle is nothing but coordination number of that particle. Am I clear, students? Let's talk about this one. This is my test particle. How many particles are surrounding it? 4. So what's the coordination number of this one? 4. This is my test particle. Test. How many particles are surrounding it? 1, 2, 3, 4, 5, 6. So what's the coordination number here? 6. Am I clear, students? Let's move ahead. Students, so mainly we have studied 7 different types of Bravais lattice, and these lattices are CTO, cubical, tetragonal, orthorhombic, empty, monoclinic, triclinic, and HR, right? Hexagonal and rhombohedral. But out of these 7 crystalline lattice, we have to study only 2 crystalline lattice in detail. The first one is cubical lattice and the second one is hexagonal. Students, let's first of all discuss in detail about this cubical lattice. Okay. Student, now let's first of all talk about a cube. If I talk about a cube, in a cube, how many corners are there? 8 corners, right? If I talk about the number of faces, 6 faces. Consider your room to be a perfect cube. Now, how many walls are there? 4 walls, 1 roof and 1 floor. So, number of faces, 6. How many edges are there? These things are referred as edges. So, how many edges? A total of 12 edges. Number of edges equals to 12. Body center. Body center is the point where the body diagonal intersects each other. How many body diagonals are there? 4 body diagonals, and these body diagonal exactly intersect at the body center. This one is the position of body center, the center of the cube. Am I clear? Next one, the number of body diagonal, it's 4. And if I talk about the number of face diagonals, student, in a cube we have 6 faces and on each face we have 2 face diagonals, right? Am I clear? These 2 are the face diagonals. So on each face, 2 face diagonals, 6 face, a total of 12 face diagonals. Am I clear? Now let's talk about the contribution of atom in a single unit cell. Student, let's suppose this is my cubical unit cell. Cubical unit cell, which on repetition in 3 dimensions is generating this entire lattice, and the lattice is cubical lattice. Now this is my cubical unit cell. If one atom is placed at the corner, it will be touched by how many atoms in the entire cube? Or it will be touched by how many unit cell? Basically, if an atom is placed at the corners, it is shared by 8 cubes. Am I clear? So it's the net contribution of this particular atom in this unit cell. It's 1 by 8. If an atom is placed at the corner, the contribution of that particular atom in that unit cell is 1 by 8. If n atoms or nc atoms are placed at the corners of a cube, the net effective number of atoms because of the placement of atoms at the corners is nc by 8. nc by 8 is the effective number of atoms coming from corners. Now, face. If an atom is placed at the face center, can I say it will be shared by 2 cubes or 2 cubical unit cell? So what's the effective part of this atom inside this cubical cell? It is shared by 2. So one will have a contribution of 1 by 2, right? If NF is the total number of atoms placed at the face center, then effective number of atoms coming from face edge is NF by 2. Am I clear? NC from corners, NF by 2 from faces. Now, body center. This body center lie exactly inside this cube. So what's the contribution of atoms from this body center? It's 1. Am I clear, students? Next, edge center. This is the edge center of this cube, right? Now if an atom is placed at the edge center, basically it is shared by 4 cubes. So in a particular cube, the net contribution will be 1 by 4. If n is the number of edges, then the net contribution of atoms coming from edges is Ne by 4. It's Nb, number of body center, 100% contribution. So this is how we calculate Z effective of an atom placed at different lattice points or different points on in a cube. Am I clear, students? Let's move ahead. Students, now if I talk about this classification of cubical unit cell, we have 3 types of cubical unit cell. First one, simple cubical unit cell. Here, the atoms are placed at corners. in such a way a particular atom touches the adjoining corner atoms. In a simple cubical unit cell, atoms are placed at corners in such a way the particular corner atom touches the adjoining corner atom. Am I clear, students? Next one, body-centered cubical unit cell. Atoms are placed at corners plus body center. Body center in such a way that the corner atom touches the adjoining body center atoms. Am I clear? Along body diagonal. We'll study about this. Corner atoms and the body center atom touches each other along body diagonal. Am I clear, students? So along this body diagonal, the corner atom, the body center atom, and this corner atom, they will touch each other. Next one, face center atoms. Atoms are placed at corners plus face center. Face center in such a way the corner atom touches the adjoining face center atom. Am I clear, students? Let's move ahead. Let's first of all talk about simple cubical unit cell. Already I have told you, atoms are placed at corners in such a way one corner atom touches the adjoining corner atoms. Am I clear, students? Okay. This is how where these atoms are placed at each and every corner of this cube. How many atoms are placed? 8 atoms. Okay. These two atoms, if I focus on this particular atom, it is going to touch this corner atom, and this one. 3 corner atom inside this unit cell. In this particular unit cell, it is going to touch 3 corner atoms. Am I clear? The adjoining corner atoms along x-axis, along y-axis, along z-axis. Am I clear? But it's not the total number of, or it's not the coordination number. I already have introduced you the coordination number. So 3 is not the coordination number. In the entire lattice, the coordination number will be different. We'll talk about that. Okay. Relationship between edge length and the atomic radius. Student, here, the corner atom touches each other along the edge length. This is the edge length and A. And now if R is the radius of atom, can I say R plus R equals to A? So 2R equals to A. So can I say radius of atom here is edge length divided by 2. What's the Z effective of this Fcc? Atoms are placed only at corners. Total number of corners 8. Contribution of each corner 1 by 8. So can I say Z effective? Effective number of atoms, or Z, equals to 8 corners. Contribution from each corner is 1 by 8. So it's 1. Right, students? Shall we move ahead? Let's move ahead. Packing efficiency. How do we calculate packing efficiency of a particular unit cell? Packing efficiency is nothing but it's the ratio of volume occupied by atoms to the volume of unit cell. The volume occupied by atoms to the volume of unit cell. Okay. So can I write this packing efficiency is Z effective into volume of one atom. Volume of one atom upon volume of unit cell. Of unit cell. Okay, what's Z effective for Fcc? It's nothing but 1. Volume of one atom, 4 by 3 pi r cube. Each atom is considered to be a hard rigid sphere having radius r. And the volume of unit cell, a cube. 4 by 3 pi r is a by 2 whole cube upon a cube. So it's pi by 6. So what's the packing fraction, student? It's 0.52. Means in a simple cubical unit cell, 52% of the space is occupied by atoms. Packing fraction is 52.4% or 0.52. And the void fraction, what's the empty space? 48% approx. 48% approx. Am I clear? Or 47.6%. Let's move ahead. Coordination number. I was talking about this only, right? Student, if I talk about the coordination number of Fcc, let's suppose this is my test particle or constituent particles for which I am going to calculate the coordination number. Student, in a Fcc unit cell, if I talk about this particular atom, at a distance of A, it is going to be surrounded by 6 particles. One along this x-axis, one along negative x-axis. So 2 along x-axis, 2 along y-axis, 2 along y-axis and 2 along z-axis. One along positive z-axis, one along negative z-axis. So what's the coordination number of for this SCC? The coordination number is 6. And basically, one particular atom will be touched by 6 atoms at a distance of A. If I talk about the next nearest neighbor after a distance of A, student, now if I increase the distance little bit, then at a distance of root 2A, this particular atom will be surrounded by 12 atoms. So the number of next nearest atom is 12. Am I clear? Which we find at a distance of root 2A, 1.414A. Next to next nearest neighbor, we find this at a distance of root 3A. If I move at a distance of root 3A from here, it is going to be surrounded by 8 number of particles. So if I talk about SCC, coordination number 6, next nearest neighbor 12, next to next nearest neighbor 8, next nearest neighbor we get at a distance of root 2A, next to next nearest neighbor we get at a distance of root 3A. Am I clear? Let's move ahead. Moving to the next type of unit cell which we have to study is body-centered unit cell. Student, here apart from corner, one of the atom is placed at body center. In such a way, the corner atom touches the body center along the body diagonal. Corner atom touches the body center along this body diagonal. This is my corner atom, and it is touching the body center atom. This is my body center atom and it's touching along body diagonal. Corner atom, it's touching the body center atom along body diagonal. Am I clear, students? Corner atom touches the body center atom along body diagonal. Okay, let's move ahead. Relationship between the edge length and the radius. The corner atom touches the body center atom along body diagonal. What's the length of body diagonal? It's root 3A. Am I clear? What's A? Edge length of the cube, edge length of the unit cell. So length of the body diagonal is root 3A. And now the corner atoms, one of the corner atom is this one, having radius R, corner atoms, and this one is the body center atom, and they all are touching. So R plus 2R plus R. So can I say R plus 2R plus R will be equals to root 3A. So what's the value of R? It's root 3A upon 4. Am I clear, students? So the relations between the radius and the edge length in case of BCC, it's R equals to root 3A by 4. R is the radius of atom. A is the edge length of the unit cell. Effective number of atoms per unit cell. Okay. Atoms are placed at corners. Total number of corners 8. Contribution from each corner is 1 by 8. 8 into 1 by 8 plus one of the atom is placed at the body center plus 1. So what is effective number of atom? It's 2, students. Am I clear? Let's move ahead. Packing efficiency. Packing efficiency we calculate as Z effective into volume of one atom, upon volume of unit cell, volume of unit cell. What is the volume of unit cell? AQ. What is Z effective? 2 into 4 by 3 pi r cube upon a cube. R value is root 3a by 4. Substitute the value of r. So it's 2 into 4 by 3 pi root 3a by 4 whole cube upon a cube. So it's 0.68 students. The packing efficiency in case of body-centered cubical unit cell is 68%. So what's the void fraction? Packing fraction is 68%. So what's the void? Packing percentage. 68% of the space is occupied by atoms, right? What's the void fraction? If I talk in terms of fraction, it's 0.32 in case of BCC type of unit cell, cubical unit cell. Okay. Next one, coordination number. Student, this is my test particle or test constituent particle. If I focus here, basically it is surrounded by 8 particles, corner particles, and it is at a distance of these 8 corner particles are at a distance of root 3 by 2a. So what's the coordination number in case of BCC? The atom which is placed at the body center is surrounded by 8 corner particles and the distance is root 3a by 2. Coordination number is 8. If I talk about the next nearest neighbor, if I move at a distance a from here, it will be surrounded by 6 particles. You can see, you can imagine your room as a perfect cubical unit cell and then consider to be a BCC structure and then try to calculate the next nearest neighbor. You will see at a distance of A, it is surrounded by 6 atoms. Next to next nearest neighbor, at a distance of root 2A, from this atom, it will be surrounded by 12 atoms. Am I clear, students? Let's move ahead. Moving ahead, the next type of unit cell that we have to study is face-centered unit cell. Okay, if I talk about this face-centered unit cell, students, here atoms are placed at corners and the face center in such a way the corner atom touches the adjoining face center atoms. Corner atom touches adjoining face center atoms. These are the corner atoms. This one is the face center atom, corner, 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 corner. These are the face center atoms. Now, this corner atom, this corner atom, this corner atom, this corner atom will touch this face diagonal atoms along this face center atoms along face diagonal. Face diagonal. Am I clear, students? Similarly here, these corner atoms will touch this face center atom along face diagonal. What's the length of the face diagonal? It's a plus under root a square plus a square. It's root 2a. The corner atoms are touching the face center atoms along the face diagonal. This one is the face diagonal. A plus a under root. The length of face diagonal is root 2a. Now, if R is the radius of atom R, this one is 2R and this one is R. So, can I say R plus 2R plus R is equals to root 2A. So, what's the value of R? It's root 2A upon 4. It's A upon 2 root 2. Am I clear, students? Okay. If I have to calculate Z effective, how do I calculate Z effective? Z effective is nothing but effective number of atoms lying inside this unit cell. 8 atoms placed at corner, contribution is 1 by 8. So 8 into 1 by 8 plus 6 atoms placed at every face center. 6 contribution is half. 6 into 1 by 2, 3 plus 1, 4. So Z effective for FCC is how much? 4. Am I clear, students? Let's move ahead. if I have to calculate packing efficiency, how do we calculate packing efficiency? Packing efficiency is nothing but PE is equals to Z effective into volume of one atom divided by volume of unit cell. What is Z effective here, students? Z effective is for volume of one atom, 4 by 3 pi r cube. 4 by 3 pi r cube upon volume of unit cell. It's A cube. Am I clear? Now, what's the relation between radius and edge length? We have, student, 4r is equals to root 2a. So r is equals to root 2a upon 4. It's a upon 2 root 2. This is the radius. So from here, if we calculate the packing fraction, it comes out at 0.74. So student, in a cubical unit cell, the maximum packing fraction is there in case of FCC. In case of FCC, we have closest packing and it's the cubical unit cell. So we say this FCC lattice as cubical closest packing. Am I clear? And what's the packing fraction? It's maximum 74%. Packing efficiency is 74%. What's the void fraction? 0.26. Only 26% of the space is unoccupied by atoms in FCC unit cell. Shall we move ahead? Okay. Student, if I talk about the coordination number, okay, suppose this is my test particle or test constituent particle. Now, if I focus here, at a distance of a by root 2, this particle is surrounded by 12 constituent particles. This particular atom will be surrounded by 12 atoms at a distance of a by root 2. Am I clear? At a distance of a by root 2, one of the particle will be surrounded by 12 particles. You can check it. Okay. Now at a distance of a, it will be surrounded by 6, and at a distance of root 3 by 2. It's not root 3 by 2 is separate. It's complete this one. A. It will be surrounded by a total of 24 constituent particles. So what's the coordination number for FCC? Coordination number is 12. Next nearest neighbor is 6, and next to next nearest neighbor is 24. The distance are for coordination number a by root 2, next nearest a, and next to next nearest it's root 3 by 2a. Am I clear, students? Let's move ahead. So these are the important parameters related to a cubical unit cell. We have studied 3 types of unit cells: simple cubical unit cell, body-centered cubical unit cell, and face-centered cubical unit cell. And we have calculated each of these parameters: number of atoms, relation between the radius and the edge length, coordination number, and the packing efficiency. Am I clear? I hope these things are crystal clear to you all. Let's move ahead. Student, moving ahead, the next parameter which we have to study is the calculation of density. How do we calculate density? Density is nothing but mass upon volume. Okay, now let's calculate the density of different types of unit cell we have studied. Student, let me first of all give you a general formula for the calculation of density of unit cell. Unit cell, it's Z effective into mass of one atom upon volume of unit cell Mass Z effective is the number of atom into mass of one atom is nothing but mass of unit cell upon volume of unit cell. It's nothing but density. How do we calculate volume of unit cell? Volume of cubical unit cell is always a cube. If it's a cubical unit cell, it's always a cube. Z effective in case of SCC, SCC, it's 1. In case of BCC, it's 2. In case of FCC, it's 4. So we have learned how to calculate Z effective. What's the mass of one atom? If M is the molar mass, then mass of one atom is M upon Na. What is Na? Avogadro number. Avogadro number, which is having a value 6.02 into 10 raised to the power 23. Am I clear, students? Please copy all these things. Moving ahead, the next question which we have on the screen is, if the radius of an atom of an element is 75 picometer and the lattice is face-centered cubic perfect, edge length of the unit cell will be. Student, in case of FCC, what's the relation between R and A? We have 4R is equals to root 2A. So A is how much? 4 into R upon root 2. So it's 2 root 2R. Am I clear? 2 into 1.4, 414 into R. And what's the radius? It's 75. So 75 into 2, 150, 150 into 1.4. It's close to 210, approx. 210, 212. Yes, fourth is the right answer, student. I hope you understood this one also. Let's move ahead. In a solid cubic lattice, P atoms are present at the corner and the body center, perfect, and Q atoms are present at face center. Then the simplest formula of the solid will be, where this P atom is placed, it's placed at corner and it's a cubic lattice. How many corners are there? 8. So 8 into 1 by 8 plus, it's also present at body center. And body, what's the contribution of body center? 1. So 8 into 1 by 8 plus 1, it's 2. The value of P equals to 2. Now Q, this Q atom is placed only at the face center. In cubes, we have 6 face, so we have 6 face center. Its face center is having a contribution 1 by 2. So for Q, the effective number of atom is 3. Now the formula P2. And what's effective number of Q? 3. So the formula of the solid will be P2Q3. Am I clear, students? Let's move ahead. In a solid, A atoms are present at corners and B at face center. If one of the A atom is removed from the corner, then the formula will be perfect. Okay. A atoms are present at corners. How many corners? 8. Effective contribution 1 by 8. So what initial number? 1. Now one of the corner atom is removed. So how many corner atoms are remaining now? 7 only. And each corner is having a contribution of 1 by 8. So what's A value? Z effective for A? Z effective for A is going to be 7 by 8. Right? Now Z effective for B. Z effective for B. B atoms are present only at the face center. There are 6 face. So 6 face center. Each face center is having a contribution of half. So 6 into 1 by 2. It's 3. Z effective for B3, A 7 by 8. So A 7 by 8, B 3. If I multiply it's A 7, B 24. Am I clear? A 7, B 24 is the right answer, student. Let's move ahead. Okay. In a solid, oh, this one we have already done it. If A atom occupy corners, B atom occupy 50% face center, perfect, and C atoms occupy 50% edge center, then the formula of the solid will be A atoms occupy corners. So what's Z effective for A? Z effective A, 8 into 1 by 8. B atoms occupy 50% face center. There are 6 face center, so it's present at only 3 face center. Z effective for B. For B, 3, and its face center is having a contribution of 1 by 2, so it's 3 by 2. Z effective for C. C atoms are present at 50% edge centers. There are 12 edges. So 12 edge center, 50% of edge center, it's 6. So C atoms are present at 6 of the edge center, and each edge center is having a contribution of 1 by 4. So Z effective for C, 6 into 1 by 4. Once again, it's 3 by 2. Formula A1, B 3 by 2, C 3 by 2. So it's A2, B3, C3. A2, B3, C3. Am I clear, students? Students, moving to the next question which we have on the screen, and the question says, an element F has Fcc structure. The molecular weight of this element is 100. Calculate the number of unit cells present in 10 gram of the sample of element M. Okay. We have to calculate how many unit cells are there. Okay. Let's calculate the mass of one unit cell. Mass of one unit cell. How do we calculate? It's nothing but Z effective, number of atoms present in the unit cell, into mass of one atom. Mass of one atom. Right, student? Okay. In case of FCC, what's the value of Z effective? Z effective is 4. 4 into 100 by Na. This is the mass of one unit cell. 4 into 100 upon Na. Now the mass of sample is 10 grams. So total mass equals to 10 gram. Let's suppose it consists of n unit cell or x unit cell. So mass of x unit cell will be, mass of x unit cell, it's going to be 4 into 100 upon Na, mass of one unit cell, into x, and that's equals to 10. So from here we can easily calculate the number of unit cell, that's 10 into Na upon 4 into 100. Right, student? And the number of unit cell which we'll get is 1.5 into 10 raised to the power 22. I hope this particular question is crystal clear to you all. Let's move ahead. Moving to the next question which we have on the screen, and the question says, an element have FCC structure in which edge length is 200 picometer. If 200 grams of elements have 24 into 10 raised to the power 4 atoms, then find out the density of solid. Basically, we have to calculate the density of this FCC unit cell. How do we calculate density? Density is equals to Z effective into M molecular weight upon Na into A cube. Right, student? Okay. They have given the edge length. A is known to us. Z effective for FCC is how much? Z effective is nothing but 4. Okay. So Z effective is given to us. Na value is known. Have they given the molecular weight? No. Indirectly they have given. They are saying 200 gram of elements have 24 into 10 raised to the power 4, 10 raised to the power 24 into 10 raised to the power 23 number of atoms. Basically 4 Avogadro number of atoms is having a mass of 200 grams. So 1 Na number of atoms will have a mass of 50 grams. And can I say the mass of 1 Avogadro number or Avogadro number of element is nothing but atomic mass or molecular atomic mass of that element or molar mass of that particular element. So what's the value of M? M is 50. M is known to me. Z effective is known to me. Now from here I can easily calculate density. 4 into 50 upon Na, 6.02 into 10 raised to the power 23 into A cube, and the value of A is 200 into 10 raised to the power minus 12 into 10 raised to the power 3. It's there in terms of gram per meter cube. We have to calculate in terms of centimeter cube. So it's 10 raised to the power minus 10 cube. Am I clear? and finally you will get this much. I hope this particular question is also crystal clear to you all. Let's move ahead. Density of an element which has FCC structure is 6.23 gram per cc. Find out the edge length. Once again, the repetition of question, and we have the formula of density. Density of FCC is equals to FCC equals to 4 into m upon Na into a cube. Density is 6.23 gram per cc. So molecular mass we have to take in terms of grams, and it's how much? 60 upon Avogadro number 6.02 into 10 raised to the power 23 into a cube, and this a has to be there in terms of centimeter. Am I clear? A cube. So from here a cube equals to 4 into 60 upon 6.02 into 10 raised to the power 23 into 6.23. Am I clear? So from here we can easily calculate the value of A, and the edge length which we are getting is approx 4 into 10 raised to the power minus 8 centimeter. Am I clear, students? Let's move ahead. Students, moving ahead, the next topic that we have to study is close packing. Students, whenever we do the packing of metals, whenever we do the packing of solids, the packing is done in such a way that the packing efficiency is maximum. We don't want maximum void fraction, we want maximum packing fraction. So whenever we do, the packing is done in such a way that the empty space remaining is minimized. Am I clear, students? Now let's try to understand how do we do the packing in different dimensions. We have packing in 1 dimension, packing in 2 dimension, and packing in 3 dimensions. We'll discuss one by one. Student, here basically each and every atom is considered to be a hard. There is one assumption. Each and every atom is considered to be a hard, rigid sphere, and each sphere is having identical shape and size. So each atom is considered to be a hard rigid sphere having identical shape and identical size. Now let's see how do we do packing in different dimensions. Student, if I talk about the packing in 1 dimension, here this is how we do packing in 1 dimension, right? The atoms are simply placed touching each other, right? Since they are hard rigid sphere, they cannot penetrate each other, right? And we have to do close packing. So this is how we can do close packing in 1 dimension. Student, if I talk about the coordination number of one atom here, let's focus on this particular atom. It's touching how many atoms? It's touching 2 atoms. So what's the coordination number? Coordination number equals to 2. If I talk about unit cell, join 2 atom, what you are getting? Line. Join 2 atom, what you are getting? Line. So basically you are going to get a line having infinite length. Am I clear? So what's the unit cell here? Unit cell is nothing but line. Am I clear, students? Each sphere is touched by 2 spheres, hence the coordination number of packing in 1 dimension is always 2. Shall we move ahead? Let's move ahead. Now let's focus on close packing in 2 dimensions. There are 2 ways through which we can do close packing in 2 dimensions. One of the way is referred as square close packing, and the other one is hexagonal close packing. Let's first of all focus on this square close packing. Student, if I talk about the square close packing, first you arrange the atoms, this hard rigid sphere, in 1 dimensions, touching each other, right? This is how we do packing in 1 dimension. Now second layer in 2 dimension, in case of square close packing, the second layer is exactly placed over the first layer. The second layer atoms or the rigid spheres are exactly placed over the first layer atoms. Am I clear? And in this way, you are going to have such type of packing. This is the perfect way of depicting a square closed packing. Student, if I talk about the coordination number here, let's see. Simply focus on this particular atom, this one. This particular atom. It's being touched by how many atoms? 1, 2, 3, 4. So what's the coordination number in the square closed packing? The coordination number is 4. Student, if I talk about the square closed packing, basically it's a repetition. So suppose if this layer is A, the second layer is also same as that of the first layer, right? Second layer spheres are exactly placed over the first layer sphere. So this layer will also be named as A only. So in 2 dimension, one of the packing is AA packing. We call it as square closed packing. The unit cell which we get from here is a square. The unit cell which we get from here is a square. Am I clear, students? Okay. The coordination number of this type of packing, or the coordination number of atoms in such type of packing is 4. Okay. Let's talk about the packing efficiency also. Student, here I am doing packing in 2 dimensions. Now if I have to calculate packing efficiency or packing fraction, how I will calculate? It's simply Z effective. Now in 2 dimensions we cannot talk in terms of volume. We have to talk in terms of area. So Z effective into area occupied by one atom upon area of the unit cell. Area of unit cell. Am I clear, students? Okay. Let's try to calculate the relation between R and A. R is the radius of atom and A is the edge length of unit cell. Okay. R is the radius of atom. R is the radius of 2R and R. So can I say basically here 4R is equals to A. 4R equals to A. Am I clear, students? Or yeah, 4R equals to A. Now we have to calculate Z effective. What's Z effective here? Student, if I talk about effective number of atom in one unit cell, it's 1, 2, 3, 4. So 4 into 1 by 4 plus 1 complete plus half of this one, half of this one, half of this one, and half of this one. So 4 into 1 by 2. So it's 2 from here, 1 from here, and 1 from here. Z effective is 4. 4 spheres will line one of the unit cell. Am I clear? Now, packing fraction. We have 4R is equals to A, one of the relation, and then we have Z effective equals to 4. So now 4 into area occupied by one atom. Area occupied by one atom is pi r square upon area of the unit cell, and area of the unit cell is how much? A square. Am I clear? Now students, 4R is equals to A, so R equals to A by 4. So 4 into pi into A by 4 square divided by A square. 4 pi A square upon 16 A square. A square cancel out. So it's 4 pi upon 16. 12 point something upon 16. 12 by 16 is 75%. So greater than 75%, less than 80%. So packing efficiency in such type of a square closed packing unit cell is square closed packing is how much? 78%. How do we calculate? We have derived these things, right? What's the Z effective in square closed packing? In AA type packing, Z effective is 4. Am I clear, students? Okay. Let's move to the next type of packing in 2 dimensions. And this type of packing is referred as AB packing. AB packing. First, once again, you have to do one thing. You have to do the arrangement or packing in one dimension. This is how we do packing in one dimension. Atoms are simply arranged in a line touching each other. Now, if we will focus on this particular layer, let's see. There are certain depressions here. There are depressions here, right? So, students, in AB type of packing, the next layer is basically placed exactly on the depression of the first layer. Am I clear? This is layer A. The next layer is exactly placed on the depressions of the first layer. Take it. Similarly, the third layer is exactly placed on the depressions on the depressions of the second layer. Second layer depressions. The third layer spheres are exactly placed on the depressions of the second layer sphere. The second layer sphere is exactly placed on the depressions of the first layer sphere. If you will see here, the first layer and the third layer will match. Again, the second layer and the fourth layer will match. See, they will exactly lie above one another. First layer, third layer, they will lie exactly along a line. You can see along a line. Similarly, the second layer and the fourth layer will exactly lie over each other. Student, such type of packing is AB, AB, AB packing. So we have AB, AB, AB packing. If I talk about the unit cell formed here, student, in this AB, AB, AB type of packing, the unit cell which we get is a regular hexagon. So it's referred as hexagonal closed packing. We have studied two types of packing in two dimensions, square closed packing and hexagonal packing. Hexagonal packing is AB, AB type packing. The second layer is exactly placed on the depressions of the first layer. Third layer exactly placed on the depressions of the second layer. Am I clear, students? Okay. So this is the unit cell. Can you comment on Z effective here? Z effective. Let's first of all focus on Z effective itself. This one. 1 exactly lie inside this unit cell. So 1 plus 1, 2, 3, 4, 5, 6. 6 atoms along the corners of this regular hexagon, and each atom is having a contribution of 1 by 3. 1 by 3 of the part, 1 by 3 part of this atom is lying inside this regular hexagon. 1 by 3 part of this regular hexagon is lying inside here. 1 by 3, 1 by 3, 1 by 3, 1 by 3. Am I clear, students? So 6 into 1 by 3. So 2 plus 1, it's 3. Am I clear? 3. Z effective is 3 here. And so the effective number of atoms in AB type packing in 2 dimension is 3. Can you comment on coordination number? Student, if we focus here, what's the coordination number? This particular atom is touched by how many atoms? 1, 2, 3, 4, 5 and 6. So coordination number is going to be equals to 6. So we have coordination number 6, Z effective equals to 3. Let's calculate the packing efficiency. So the coordination number is 6. Packing efficiency is 90%. Let's even derive it. Once again, it's a 2 dimension. So we will calculate packing efficiency in terms of area. It's Z effective into area of one unit cell of one atom, not unit cell, divided by area of unit cell. Area of unit cell. Now, what's Z effective, student? Z effective is 3 into area of one atom. It's pi r square upon area of the unit cell. It's root 3 by 4 into a square into 6. Why? A hexagon is basically consisting of 6 equilateral triangle. So area of hexagon is nothing but area of 6 equilateral triangle. Now, what's the relation between R and A? If we look here, the atoms simply touch each other along the edge length, right? So can I say 2R equals to A? We have 2R is equals to A. So R equals to A by 2. Now, so it's 3 into pi into A by 2 whole square upon root 3 by 4 into 6 into A square. Upon 4, these terms will cancel. A square will cancel. So it's basically 3 pi upon 6 root 3, right? And it's nothing but 2. So basically it's pi upon 2 into root 3. Root 3 is 1.73. So it's 3.14 upon 3.46, right? Close to 90%. 0.9 is the packing fraction. What's the word fraction here? 0.1. So basically, students, whenever you have to do close packing in 2 dimension, which one will you choose? Square close packing or hexagonal close packing? You're going to choose hexagonal close packing. Am I clear? Let's move ahead. Let's discuss on this close packing in 3 dimension. If I talk about the close packing in 3 dimension, once again we have 3 different types of packing. One is AAA packing, so cubical packing or simple cubical packing. The other one is AB type of packing in 3 dimension, that is referred as hexagonal close packing. And the third one, ABC packing, that is FCC unit cell we will get from there. Let's see how the packing is done. Student, in this cubical or simple cubical close packing, first the atoms are arranged in 1 dimension along x-axis, then along y-axis, atoms are exactly placed, the second layer atoms is exactly placed over the first layer. Am I clear? The second layer spheres are exactly placed over the first layer, but here now I am going to place these spheres along y-axis, right? So now we have done the packing in 2 dimensions, one along x-axis, the other along y-axis. And if you will see, it's nothing but a AA packing, square close packing. Now I am going to place the third layer along length, width, and now along height, so along z-axis. Now student, the third layer sphere is exactly placed on this sphere, AA sphere layer. Am I clear? Now I am moving along this axis, z-axis. The third layer sphere is exactly placed over these layers. The type of unit cell which we get from here is simple cubical unit cell. This is the unit cell which we get from here. The type of packing which we say, it's AAA packing. First layer along x-axis, second layer square close packing, and after placing this third layer AAA packing, the unit cell which we get is simple cubical close packing. Student, this is the unit cell, and here what do we have already studied the properties of these unit cells. This unit cell, right? The atoms are exactly at the corners, and the corners atom touches the adjoining corner atoms. Am I clear? So if I focus on this particular atom, it will touch this one, and this one. One along x-axis, one along y-axis, and the other along z-axis. In one of the unit cell, in the entire unit cell, one of the particular atom will be touching 6 atoms. One of the atoms will be surrounded by 6 atoms at a distance of A. So what's the coordination number here? What is the coordination number in simple cubical unit cell? It's 6. Am I clear? What's Z effective? Since the atoms are exactly at the corners, each corner is having a contribution of 1 by 8. So Z effective 1. That's 8 into 1 by 8. Packing fraction? 52%. We have studied it. Even we have derived these things, right, students? Let's move ahead. Effective number of atoms in the unit cell is 1, coordination number is 6, packing efficiency is 52%. The unit cell which we get is simple cubical closed packing, Fcc packing, right? The type of arrangement is referred as A arrangement. This one is also really important. Most of the times questions are directly asked on these informations. So students, now let's move ahead. Now, the second type of cubical packing, the second type of packing in 3 dimensions, and that is referred as AB packing. ABA we can say. ABA. So we will have AB type of packing here. It's similar to close packing in 2 dimensions when we were doing hexagonal arrangement. Am I clear? Let's focus here. Student, here also the first layer is simply placed along x-axis, right? One dimensional arrangement. Along a line, the first layer atoms are arranged. Now, the second layer is the arrangement of second layer is done along y-axis. This is along x-axis. Now, second layer spheres are placed along y-axis. If I talk about the arrangement along y-axis, the spheres are exactly placed on the depressions formed by the first layer. The second layer sphere is exactly placed on the depressions formed by the first layer. Second layer. Third layer. Exactly placed, the third layer sphere is exactly placed on the depressions formed by the second layer. So till yet students, we have done the packing along x-axis and along y-axis, and basically till yet we have done AB packing in 2 dimensions. And basically if I do AB packing in 2 dimensions, the type of unit cell we'll get is regular hexagon. Now we have to place the third layer, right? The packing in the third dimension along z-axis. Let's see how do we do it. Students, now if you see, the first layer arrangement is done like this along x-axis. Second layer arrangement, the second layer spheres are exactly placed on the depressions of first layer, and this is how we place the second layer. A layer, B layer along y-axis. A layer is done along x, B layer along y. Now we have AB. Now we have to place the third layer along z-axis. How do we place? If you see this AB packing, you are going to get 2 types of void, and these voids are basically triangular voids, right? One of the void is B type and the other void is C type. Are you seeing it? B type void and C type void. These are basically your triangular void. I say it as upper triangular void and lower triangular void. Now students, basically in close packing in 3 dimensions, in AB type packing, the third layer is exactly placed on one of these triangular voids, and basically if I do the packing along z-axis, I prefer to cover all the lower triangular voids, or even you may cover the upper triangular void. Here also basically I have covered the lower triangular void. You can see this is my third layer, and in this third layer I have covered this void B of the type B, and this B was lower triangular void. So A, B, and in the third layer along z-axis, basically I am covering the lower triangular voids. I hope you understood till here. Now let's see what happens when I cover this lower triangular void. Basically we get a structure like this. This is my first layer in 2 dimensions, right? All these pink spheres are basically the first layer arrangement done in the first layer. Now exactly on these first layers we have covered the lower triangular void, and this yellow marked spheres are the second layer sphere. Student, as soon as I place the sphere along z-axis to cover the lower triangular void, now in this given arrangement, what we will see, we'll have two types of void once again getting formed. One is the C type of void, and one is once again this triangular void. Although this C type of void is somewhat different, we'll focus and we'll study about this C type of void after few minutes. But right now, simply focus on this pink type of void. Now, what I have to do, I have to place the third layer on this pink type of void. And if I place the third layer on this pink type of void, basically I am going to place the sphere here. And if you'll see here, if you cover all the pink type of voids, basically what you will see the first layer and the third layers exactly matches. So I'm having A, then B. In layer B, basically we have covered the lower triangular void. After covering the lower triangular void, we were getting two types of void. One is upper triangular void, that was the pink void, and the other one was C type of void. We don't need to bother about the C type of void. Now once again I am going to cover this upper triangular void, and as soon as I cover the upper triangular void, the third layer will match with the first layer. So such type of packing is AB, AB, AB packing. Student, now if I focus on the unit cell here, the type of unit cell which we get is hexagonal close packing. Close pack. It is referred as Fcc unit cell. So if I do packing in 3 dimensions, and if it's a AB, AB, AB packing, then the unit cell which we get is HCP. Am I clear? Now let's focus on this unit cell. Student, okay. This was my first layer. Now, if you focus on this particular diagram, let me erase all these things. Okay. And now, simply focus here. So this is my first layer, right? Okay. This is my unit cell, a regular hexagon, right? In 2 dimensions, whenever I do AB, AB type packing, the unit cell is a regular hexagon. Now I am going to do the packing in 3 dimensions. This is my second layer, the yellow spheres. And in this regular hexagon, how many yellow spheres you are seeing? 1, 2, and 1, 3. Am I clear, students? Basically, you are going to see almost 3 yellow spheres in this one regular hexagon. So in second layer, how many spheres will be there in the unit cell? 3 spheres. Now, in the third layer is the repetition of first layer. How many spheres will be there? Once again, 6 spheres. So student, if I talk about this AB type of unit cell, we'll have 6 spheres, 1 sphere exactly at the center, surrounded by 6 spheres. Now at the central sphere, we'll have 3 spheres touching this central sphere, and in the third layer, once again, we'll have 6 spheres surrounded by 1 central sphere. Let's see. 6 spheres, 1 central sphere. Exactly on the central sphere, all these 3 spheres will lie. All these 3 spheres will lie exactly at this sphere. And now, this particular central sphere will exactly lie over here. Am I clear? And now this particular central sphere in the third layer, in the layer once again A, it is surrounded by 6 spheres. Am I clear? 6, 1 central, 3, 6, 1 central, 3, 6, 1 central, 3, 6, 1 central, 3. Am I clear? This layer is A layer. In B layer, only 3 spheres are there, and these 3 spheres exactly fit inside the unit cell. Once again, 6 sphere A, 3 sphere B, 6 sphere. Sorry, this one is A, B, A. Am I clear, students? Now, let's focus on the Z effective. Student, if I talk about this Z effective, how do you calculate? What do you say? 3 spheres exactly inside the unit cell here. So 3 from second layer. Now the central sphere, this is the first center, right? And first center will be shared by 2 unit cell. So one will have a contribution of 1 by 2. And how many central atoms are there? One here and one here. So 2 into 1 by 2. 4 plus 6 spheres surrounding these central sphere. So 6 from here and 6 from layer A, the top layer and the bottom layer. Both these layers, 6 spheres, and each sphere or the contribution of each sphere will be how much? 12 into 1 by 6. Each atoms will be shared by 6 unit cell. So what's the Z effective you are getting here? 3 plus 1, 4 plus 2. What is the Z effective, students? In case of HCP unit cell, the Z effective is 6. 3 from layer B, 2 into 1 by 2 from first center or the central sphere, and 12 the neighboring sphere. Am I clear? Okay. Now let's focus on the coordination sphere, coordination number. Let's focus on this sphere itself. It's surrounded by 6 sphere from this layer, 3 sphere from the top layer, and 3 spheres from the bottom layer. Am I clear? This one 6 from this particular layer, 3 from layer B, and exactly 3 from layer B once again from the bottom side, right? So 6 plus 3 plus 3. So what is the coordination number of a HCP unit cell? The coordination number Cn is going to be equals to 12. Am I clear? I hope these things are crystal clear. Each sphere is touched by 12 other spheres in 3 dimensions. 6 in one layer, 3 in the top layer, and 3 in the bottom layer. Right, students? I hope the things are crystal clear. 6, 3, 6. Once again, 3 from here also. Right? Student, if I talk about the packing efficiency, the packing efficiency is once again 74%. We have studied a similar packing efficiency where in case of FCC unit cell, in case of cubical FCC unit cell, right? And here in HCP also, the packing efficiency is 74%. There is one derivations. Basically, how do we calculate packing efficiency? In 3 dimension, it's Z effective into volume of one atom upon volume of unit cell. How do we calculate volume of unit cell? Area of the unit cell into height. And what's the area here? 6 equilateral triangles. So 6 into root 3 by 4 a square into height of this hexagonal unit cell. Am I clear? This is how we calculate volume. And volume of atom you can easily calculate 4 by 3 pi r cube. Z effective is how much? 6. So 6 into 4 by 3 pi r cube, 2r equals to a. So from there you can easily calculate packing efficiency. Am I clear, students? So packing efficiency 74%, coordination number 12, Z effective equals to 6. On these things questions are directly asked. So please note down all these things. Students, now let's focus on the third type of arrangement that we do in 3 dimensions. And this particular arrangement is referred as ABC ABC arrangement. A, B, C, A, B, C arrangement. Student, already we have studied this AB arrangement in 3 dimensions, right? AB arrangement in 3 dimensions, and it was giving us HCP. Right? So we know how to arrange the layer B. Layer B is basically placed on the lower triangular void formed by layer A. Now as soon as I place the layer B, now we see 2 types of void. One of the void is the pink void and the other void is C type of voids, right? We have seen here the pink void and the C types of void. Now students, in ABC type of packing, the third layer is placed to cover this C type of void. The third layer is placed to cover this C type of voids. Let's see. The third layer is exactly placed on these C types of voids. As soon as I place this third layer, now I am getting once again two types of void. One this one, and once again upper triangular void. Student, now in the fourth layer, how we will cover this fourth layer? The fourth layer will exactly be placed on the pink voids. Basically, it's nothing but a octahedral void. So students, in ABC type packing, the layer B is placed on layer A to cover the lower triangular void, and layer C is basically placed on layer 2 to cover the octahedral voids. Am I clear? Now, the fourth layer is placed on the third layer once again to cover the octahedral voids. This one. As soon as we cover the octahedral void once again, the first layer and the fourth layer will match. So I will have A, B, C, A. Here we are covering the octahedral void, and here also we are covering octahedral void. Where we are covering lower triangular void. Am I clear, student? If I talk about the type of unit cell which we get here, student, here we get Fcc unit cell. Let's see. This is how we do close packing in 3 dimensions. You might have gone to a fruit market. Stacking of orange. Basically, stacking of orange is done like, or stacking of fruits is done like this only. Because in this type of packing in 3 dimensions, we have maximum efficiency, maximum packing fraction, right? We have studied in FCC. The packing fraction is 74%, and here the type of unit cell which we are getting here is FCC. So in this type of packing, the packing efficiency is 74% maximum. So it is referred as cubical closest packing or FCC packing. Am I clear? Okay. Let's talk about these things in a detailed way. This is my layer A, layer B, layer C, and the first layer and the fourth layer exactly match with one another. Am I clear? These things are not that important for JEE mains and NEET. For JEE advanced, sometimes this particular diagram or planes are asked, planes related to FCC, but don't worry. Once this JEE mains is over, I'll discuss all these things in a more detailed way. Okay. So let's move ahead, student. Coordination number we have studied. In case of FCC, one atom is surrounded by 12 atoms, right? At a distance of A by root 2. What's the packing efficiency? 74%. What's Z effective? Z effective is 4, right? We've studied all these things. Okay, let's move ahead. This was related to BCC, but that's not so important. Student, this is the summary of close packing in 3 dimensions. This SCC is important, CCP is important, and HCP is important. This BCC is not important because it's not a close packing. Here, the packing is not a close packing. So I have not discussed BCC type of arrangement because right now we are only focusing on closed packed structures. So this BCC is not a closed packed structure. And we have studied all these parameters related to SCC, FCC, and HCP. Am I clear, students? Please copy it. Students, just now we have seen whenever we were stacking the solids and whenever we were doing the close packing of solids, we were getting some voids. We were getting triangular voids. We have some more important type of voids. The first one is tetrahedral void and the second one is octahedral void. We have studied triangular void also. How a triangular void is formed? It's simply formed like this. 3 spheres touching each other and forming a triangular pattern. Here the void we are getting is a triangular void. Student, now we have to understand how do we get a tetrahedral void and how do we get octahedral void. Let's try to understand. This one, tetrahedral, tetrahedral, octahedral, but how do we get it? Let us try to understand. Student, in order to get a tetrahedral void, what you need to do, take three spheres, arrange them in such a way that the three spheres should touch each other. Right? They are forming a triangular pattern. They are placed in the form of this equilateral triangle, right? Okay. They are touching each other. Now, if you focus here, students, as soon as I place these three spheres touching each other, what we are seeing, we are observing one type of triangular void here, right? Now I have to take the fourth sphere. I have to take the fourth sphere, and this fourth sphere is exactly placed to cover this triangular voids in such a way that the fourth sphere should touch all these three spheres. Take three spheres touching each other, place the fourth sphere in such a way, first it should cover this triangular void and then it should touch all the three spheres. Am I clear? Now look from the side view. Have a side view. Look from this side. Look from this side. Am I clear? The type of void which you are going to get is referred as tetrahedral void. Three spheres touching each other. Place the fourth sphere exactly on these three spheres. Look from side view. You are going to get a tetrahedral void. Am I clear, students? Now, octahedral void. Students, just now I was talking about this octahedral void. Now let's have a brief discussion about this octahedral void, how it's formed. Student, we have studied chemical bonding, right? And there we have studied octahedral geometry. How do we form an octahedral geometry? SF6, right? Sulfur, fluorine at 4 fluorine atoms at the equatorial position. So you have to take 4 spheres touching each other. So they are going to form a square pattern, right? Now, you are going to get a void here. One void, right? Now, you take 2 spheres. Try to cover these voids from the top as well as from the bottom. So you are going to take 4 spheres touching each other in a plane. One void is formed. Place one sphere exactly from the top and the one sphere from the bottom to cover this void. Now, look from the side view. Have a look from the side. You are going to get a octahedral void. Student, there is one more way of getting octahedral void. Take 3 spheres, form a lower triangular pattern like this. Take 3 more spheres, arrange them in such a way they should touch each other and form a upper triangular pattern. Then merge them. You are going to get a octahedral void. Am I clear? But the best way is this one. Take 4 spheres in the plane, place one sphere from the top, one sphere from the bottom, have a look from the side view. You are going to get a octahedral void. Am I clear, students? Okay. So this one, 3 spheres forming a lower triangular pattern and 3 spheres, this one. These 3 spheres have formed a lower triangular pattern and 3 spheres have to form a upper triangular pattern. Let me focus here. This one, and this one is forming a upper triangular pattern. This one, and this one is forming a lower triangular pattern. And now one octahedral void is formed here. Am I clear? Similarly, let's have a look at the tetrahedral void. 1 sphere, 2 sphere, 3 sphere touching each other, and the 4th sphere, this particular sphere, is exactly placed on the triangular void. As soon as I cover this triangular void, and if I look from the side view, I am going to get a tetrahedral void. Is this clear, students? Let's move ahead. Students, now let's try to understand the position of tetrahedral and octahedral voids in FCC. For this, I am giving you a simple trick. Consider your room to be a perfect cube and consider it's having a FCC arrangement. If it is having FCC arrangement, atoms are placed at the corners as well as at the face center. Okay. From corner, what's the distance to this face center atom? It's a by root 2. Right, students? Okay. Now, simply focus on 3 walls. This face, the adjoining this face, and the row. Focus on the atoms placed here. One of the atom is placed here, the other one is placed here, and the third one is placed here, right? What's the distance between these two sphere? It's also a by root 2. You can easily calculate, right? This one to this one distance also a by root 2. Now, if this particular atom is touching the corner atom, which is at a distance of a by root 2, means this face center atom will also touch all the adjoining face center atoms. This one will touch this one also and this one also. Am I clear? Now, one sphere, and one sphere touching each other, forming a triangular pattern. Can I say the fourth sphere, which is placed at the corner, will also touch these spheres? Because in FCC, the corner atom touches the adjoining face center atoms, right? So this corner atom will touch these face center atoms. And can I say it will exactly lie above these 3 atoms? Now, if I look from the side, I'm going to get a tetrahedral void. So students, basically in FCC, along every corners, I'm going to get a tetrahedral void. How many corners are there? 8 corners. So how many tetrahedral void I'm going to get in FCC? 8 voids. 8 tetrahedral voids in FCC, which will lie along each corner at a distance of root 3 by 4a from each corner. Okay, basically students, we are having 8 corners. These 8 corners are joined by 4 body diagonals. So students, basically this tetrahedral voids will lie on this body diagonals. On each body diagonal, I will have 2 tetrahedral voids at a distance of root 3 by 4a from each corner. At a distance of root 3 by 4a from each corner. From here, I will have one TV here, one TV here. And these TV is not television, it's tetrahedral void. These TV will lie exactly inside this room. So what's the effective number of tetrahedral void? Effective number of tetrahedral void is how much? 8. Am I clear? Now, student, if I talk about the position of octahedral void, you can simply understand it like this. Students, in case of octahedral voids, if there is a void, basically it is surrounded by 6 atoms, right? 4 along the plane, 1 above the plane, 1 below the plane. Now focus on body center. If one of the atom is placed at the body center in FCC, it will be surrounded by how many atoms? 4 adjoining walls, 1 top and 1 bottom. So students, in FCC, one of the octahedral void is formed at body center and remaining octahedral voids are formed at edge center. Students, there are 12 edges. Each edge is having a contribution of 1 by 4. So what's the total number of octahedral voids? 12 into 1 by 4 plus 1. 12 along each edge center, each edge having a contribution of 1 by 4. So 3 net effective number of octahedral voids from edges, 3 effective number of octahedral voids from body center, 1. Total 4. Am I clear? Okay. All these things we have studied, right? Okay, student, one more thing. If I talk about the nearest distance between the 2 tetrahedral voids, this one is also important. It's a by 2. It's a distance, this is the TV, which is at a distance of root 3 by 4a from each corner, root 3 by 4a from each corner, 4a from each corner, and the nearest distance between these 2 TV is nothing but a by 2. Am I clear? Okay. Okay, one more thing. In cubical closest packing, the effective number of tetrahedral void is 2 times Z effective. In a cubical closest pack or in any type of closed packing, the number of tetrahedral voids, Number of tetrahedral voids, number of TV is always equals to 2 into Z effective. Am I clear? Please copy these things. Position of octahedral voids, I've already discussed, one at the body center and then along at the center. At the center, at the center, at the center, at the center, at every edge center, and each edge center is having a contribution of 1 by 4. So 12 into 1 by 4 plus 1 at the body center, 3 plus 1. In FCC, effective number of atoms is 4. Effective number of octahedral void is 4. Am I clear? It's formed at every edge center and 1 at the body center. Shall we move ahead? Okay. All these things we have done it, right? Number of octahedral void is 4. Number of tetrahedral void is 8 students, right? Let's move ahead. Now, this is also really important, not for NEET mainly for JEE mains or JEE advanced, the position of tetrahedral and octahedral void in HCP. Basically, students, above and below its sphere there is a tetrahedral void, hence the number of tetrahedral voids in HCP is 12. Z effective is 6, and we have studied in closed packing the number of TV is 2 times Z effective. So number of TV is 12 in case of HCP. Other than tetrahedral voids, all the voids are octahedral voids, and the number of octahedral voids is also 6. In any closed packing of maximum efficiency, there are 2 TV and 1 OB per particle per Z effective. Am I clear? Please copy all these things. Let's move ahead. Student, now let's discuss some questions related to the concept which we have discussed. Okay. In solid oxide, O2 minus are arranged in CCP. Perfect. Cations of A occupy 1/6 of tetrahedral voids and cation B occupied 1/3 of octahedral void. The formula of oxide will be perfect. Students, I'm having O2 minus and it's arranged at CCP. O2 minus. It is arranged at CCP. What's Z effective for the CCP? Cubical closest packing? 4. Z effective for O2 minus, it's going to be 4. Right. Cation A occupy 1/6 of the tetrahedral void. A. What's Z effective for A? Student, if I talk about Z effective for A, it's 1/6 of tetrahedral void. How many tetrahedral voids in FCC? 8. So 1/6 into 8. It's nothing but 4/3. Right? Whereas cation B occupy 1/3 of the octahedral voids. Z effective for B. How many octahedral voids are there in FCC? 4. 1/3, 1/3 into 4. Once again, it's 4/3. Formula A 4/3, B 4/3, O 4. Am I clear, students? Now, so can I write it as A4, B4, O12? If I take common 4 as common, the empirical formula is going to be A, B, O3. And this is my answer, right? I hope this particular question is also crystal clear to you all. Let's move ahead. In a compound, atom B occupies HCP packing. A is present in 2/3 of the octahedral void. Then the formula. Okay. I'm having a compound AB. Student, if I talk about Z effective of A here, what's Z effective of A? A is present in 2/3 of the octahedral void. It's HCP packing. In case of HCP packing, the number of octahedral void is 6. So 2 by 3 into 6. It's 4. Z effective of B. In a atom B occupies HCP. Z effective for this HCP is 6. So Z effective for B is 6. Formula A4B6. It's going to be A2B3. Am I clear, student? Taking 2 common. 2 into 2, 2 into 3. So A2B3 is the right answer. Let's move ahead. In a closed packed structure, X atoms are arranged in CCP, perfect. Y atoms in every tetrahedral voids and Z atom in every octahedral void. Then find the simplest possible formula if all the atoms are removed along any body diagonal. Perfect. One of the best questions, right? Let's discuss it. X atoms are arranged in CCP. CCP. Perfect. Initial Z effective for this X is going to be 4. Right? Initial Z effective for Y. It's there in every tetrahedral void. And number of tetrahedral void is 8. So effective number of Y is 8. Right? Z atoms are there in octahedral void. Z atoms are there in octahedral void. Now, in case of FCC, what's the number of octahedral void? 4. So initial condition is X4, Y8 and Z4. Now, atoms are removed along the body diagonal. So if I talk about this X, will there be any loss? Yeah. There are 2 corner atoms. Each corner is having a contribution of 1 by 8. How many corner atoms now remaining? 6 only. So what's the effective number of X? Z effective for X. After removal of 2 atoms along body diagonal. Z effective for X. It's 3 plus 1 by 8 into 6. 3, 4. 3 plus 3 by 4. 15 by 4. Right? This is Z effective for X. Now Y. Student, this Y is tetrahedral void. Basically on every body diagonals, we are having 2 tetrahedral voids. So how many Y's are removed? 2. Initial A, 2 removed. So Z effective for Y is 6. Z. This Z is nothing but octahedral void. And one of the octahedral void is there at the body center. So if I am removing that, basically I am removing one of the octahedral void which is placed at the body center. Initial number of octahedral void 4. 1 I have removed, so it's 3. Formula X 15 by 4, Y 6, Z 3. So it's X 15, Y 24, Z 12. Student, if I take 3 common, it's going to be X5, Y8, Z4. X5, Y8, Z4 is the right answer for this particular question. Student, now let's move ahead. Now let's talk about ionic crystals. In ionic crystals, we'll have the constituent particle as ions, cations, anions. Which one is larger in size? Anion. So size of anion greater than the size of cation. So student, in general, the anion will occupy lattice site. Anion will occupy lattice site, whereas cations will be placed in the voids. Now we have different types of voids, right? Triangular voids, tetrahedral voids, octahedral voids, cubical voids. So now we have to calculate the size of cations which should be placed in these type of voids. Or basically from here we can also comment on the size of the voids which we make it. Okay. Let's first of all focus on triangular void. How do we get triangular void? 3 atoms are placed in such a way that they touch each other. Let's assume these 3 are anionic sphere. Anionic sphere. Now the minimum As soon as these anionic spheres are placed, I'm going to get a triangular void like this. Now we have to calculate the minimum size of cation which should be placed in this triangular void in such a way that it touches all the three spheres, all the three anions. So basically the coordination number of this cation has to be 3, and in that case I have to calculate the size of cation. Okay, the structure is like this. Anion, let's suppose it's having a radius r, and the cation is having a radius small r, right student? Now okay, this r, and from here to here, can you tell me the distance? From here to here it's r, and from here to here it's small r. So r plus r is this particular length. Am I clear? Now students, I can use trigonometric formula. This one, angle 30 degree. So base hypotenuse cos 30 equals to r, that is base upon hypotenuse. This small r is the radius of cation which is placed in this triangular void, so that it's having a coordination number 3, so that it's touching 3 anions. Now student, from here this cos 30 value is how much? Root 3 by 2 is equals to r upon r plus r. If I solve it, the radius ratio r upon r value which we get is 0.155, right? So if the radius of cation is 0.155 times the radius of anion, it will touch all these three spheres. The minimum size of the cation has to be 0.155 times the radius of anion in order to have coordination number 3, right? This radius ratio has to be 0.155, sorry, radius of cation upon radius of anion. The minimum size in order to have a coordination number 3 has to be 0.155. If I increase the size of the cation, will it still touch? Yeah. Now these three atoms won't touch, but this particular cation may still touch. Am I clear, students? Okay. Moving to the next one, tetrahedral voids. How do we get a tetrahedral voids? 3 atoms placed in spheres in such a way they are forming, they touch each other. The fourth sphere is exactly placed to cover the triangular void. Now if I look from the side, I am going to get a tetrahedral void. Now students, here basically I am placing this cations in the tetrahedral void. What's the coordination number of this cation? If it has to touch all the 4 anions, the coordination number will be 4. All the anion touches each other and the coordination number of cation is 4. Right. In order to have a coordination number of cation equals to 4, what should be the minimum size of cation? Right? Let's try to calculate it. Student, here basically we are having a tetrahedral geometry. We have studied it, right? A tetrahedral geometry is like this. Am I clear? What's the bond angle? The bond angle is 109 degree. And here the cation is placed exactly at the center. Right, student? So if I talk about this particular length, these two spheres will touch each other. It's nothing but r plus r. One sphere placed here, one sphere placed here. It's r plus r. And this particular length, from here to here it's r, and from here to here it's r. So it's r plus r. Right, student? Now, and this angle is 54.5 because the bond angle is 109. This one perpendicular, hypotenuse. R upon r plus r equals to sine 54.5 degree. Sine 54 is having a value of 0.81 close. So from here, the value of r by r which we get is 0.225. This relation is really important. The size of tetrahedral voids is always 0.225 times the size of atoms, or the radius of cation which should be placed in this tetrahedral voids in order to touch all the four sphere has to be 0.225 times the size of atom. It should be the minimum size of cation. Am I clear? R plus upon R minus, the minimum size has to be greater than or equals to 0.225. If I further increase the size of cation, still it may touch, but the anions will not touch each other. But I need to focus on this cation only. I am bothering about the radius ratio or the coordination number of cation. Still it may touch, right? If it's further increased. So student, we'll talk about the limiting radius ratio. Don't worry. Okay. But before that, let's discuss few more cases. Octahedral voids. Student, in the same way, right? Four atoms placed along the plane, forming a void. The fifth atom is placed up from the top, sixth atom is placed from the bottom. Now you are having an octahedral void, right? And this is how we get it. Now in this octahedral void, one cation is placed. We have to calculate the radius ratio of this cation. What's this length? R, and this small length, small r. This one is R, and this is 45-degree angle, right? So can I say R upon R plus R is cos 45? What's cos 45? 1 by root 2. So student, from here, R upon R value which we will get, in order to have a coordination number equals to 6 equals to 0.414. The minimum size of cation in order to have coordination number 6 should be 0.414 times the size of atom, or even we say it as the size of octahedral void. Size of octahedral void of OV equals to 0.414 times size of atom. Size of octahedral void is 0.414 times size of atom. Am I clear? Let's move ahead. If I talk about the cubical void, here students, here this cation will have a coordination number of 8. And when do we get such things? When all the atoms, all the anions are placed along the corners exactly at the body center, I will have one void. And now my cation is placed exactly at the body center. If it's placed at the body center, it is going to touch all the corner atoms or all the anions. Am I clear? Student, here the radius ratio R upon R, the minimum size of cations in order to have a coordination number 8 has to be 0.732 times the size of atom. 732 into R. R upon R has to be equals to 0.732. Or I can say R upon R should be greater than equals to 0.732. In order to have a coordination number 8. Am I clear? Student, now let's talk about this limiting ratio, the summary part. Okay, for a coordination number 3, what should be the minimum value of R upon R? The minimum value has to be 0.155. For coordination number 4, what should be the minimum value of radius of cation upon radius of anion? 0.225. So students, if R upon R is lying between 0.155 to 0.225, greater than equals to 0.155, less than 0.225, in this case, the cation will have a coordination number 3. Similarly, in order to have a coordination number 4, the radius ratio should lie in this range. Minimum 0.225, maximum 0.414. If it's 0.414, in that case, it will be a octahedral coordination number 6. Am I clear? Okay. For coordination number 6, the minimum radius ratio has to be 0.414. And maximum should be less than 0.732. And in case of cubical voids, the minimum size of cations which should be placed in order to have a coordination number 8 should be 0.732 times the radius of atom, and maximum it may go up to 1. So this is the radius ratio of cation and anions in order to have different types of coordination number or different coordination number. With increase in the radius ratio, the coordination number also increases. Am I clear, students? These things are quite important. So please go through this table very carefully. If cation is placed in a cubic void and edge length of the crystal unit cell is 390 picometer, R plus is 150 picometer, then R minus will be, okay, I'm having a cubical unit voids, cubical void, right? So atom is placed, the cation is placed exactly at the body center, right, student? This is the size of, this is the cation. Now anions placed here, anions placed here, right? This is the radius of anion, R. I hope these things are clear, students. Now we have, can I say R plus 2 into radius of cation plus R, and that's equals to root 3a, right? Student, edge length is given and it's how much? 392 picometer. So root 3 into a value is 390, and that's equals to 2R plus 2R. This 2R data is also given. The radius of cation, how much? 150 picometer. So 2R is 300 picometer. So student, 2 into radius of atom equals to root 3 into 390 minus 300 picometer, pm, right? Okay. Root 3 into 390, 1.7, 1.73 or 1.73 into 390 minus 300 equals to 2R. 4 minus 300, so it's how much? 374. 2R equals to 374, so R equals to close to 187. Do we have the option? Yeah, 187 picometer. I hope this particular question is crystal clear to you. Shall we move ahead? Okay. Two ions A plus and B minus have radius 86 and 200 picometer in a closed packed crystal of AB compound. Then find out the coordination number of cation. Perfect. A plus upon B minus, what's the size? What's the radius ratio? It's 86 upon 200, right? So it's 43 upon 100. So it's 0.43, right, student? If R upon R is greater than 0.414, in that case, the coordination number is 6. We have studied it. Octahedral void. Cation is placed here in this octahedral void. So what will be the coordination number? 6. I hope this particular question is also crystal clear to you all. Students, now let's discuss the different types of ionic crystal. Basically, I classify this ionic crystal in 3 types. AB type, AB2 types and A2B types. First, let's focus on AB types. Students, in AB types of ionic crystal, once again we have 3 types. One, rock salt structure. The second one, zinc blende structure. And the third one, cesium halide structure. Let's focus on these structures one by one. First, rock salt structure. The formula is NaCl. NaCl. Ions Na and Cl minus. Can you tell which one is having a larger size? Cl minus, right? Okay. So student, in this rock salt structure, the anions occupied CCP lattice. Anions are placed in Fcc lattice. Am I clear? Anions are placed in the Fcc lattice, whereas cations, being smaller, will be placed in voids, and here the cation Na plus is placed in all the octahedral voids. Am I clear? Cl minus in Fcc lattice, FCC lattice, Na plus in all octahedral voids. Now, what's Z effective for this Cl minus? In case of FCC lattice, Z effective is 4. So how many Cl minus? 4 Cl minus in this one unit cell. How many Na plus? Student, the effective number of octahedral void is effective number of atoms. So we will have 4 Na plus also. So in one unit cell, we have 4 Na plus and 4 Cl minus. What's the atom ratio? 1:1. That's why it's called AB type. Am I clear? Cations placed in octahedral voids, anions placed in FCC lattice, right? Okay. So student, this is the position of anion, and this is the position of cation. And they will touch each other, right? So can I say for NaCl 2 into radius of Cl minus plus radius of Cl minus plus radius of Cl minus, 2 into radius of Cl minus plus 2 into this radius of Na plus will be equals to edge length A. Am I clear? Student, one more thing you know, the size of octahedral void is 0.414 times the size of atoms. So R of Na plus in general upon R of Cl minus is in the order of, or is in the ratio of 0.414. Right? One more important point. If I talk about coordination number, Na plus is placed in the octahedral void, and if a cation is placed in octahedral void, it will be surrounded by 6 anions. So what's the coordination number? Cn of Na plus equals to 6. Similarly, the Cn of Cl minus will also be 6. Basically, one Cl minus will be surrounded by 6 Na plus and 1 Na plus will be surrounded by 6 Cl minus. Am I clear, students? So this is a brief discussion about this rock salt structure. Each Na plus is surrounded by 6 Cl minus, each Cl minus is surrounded by 6 Na plus. Cn of cation Na plus equals to 6, Cn of anion Cl minus equals to 6. Right? Now, effective number of Na plus and Cl minus is 4. The number of formula units is equals to 4, 4 Na plus and 4 Cl minus. Density we can easily calculate. Edge length already I have told you. Anion, cation, anion. 2 into R of anion Cl minus, R of Cl minus 2 into R of Na plus has to be equals to edge length. At the same time, R of Na plus upon R of Cl minus has to be equals to 0.414, right? All these things I have told you earlier only. Shall we move ahead? Let's move ahead. But before that, please copy it. 6:6 coordination number. The next type of AB structure that we have to study is zinc blende structure. Zinc blende structure. Student, Zn structure. Here, the cation is Zn plus 2, anion is S2 minus. Here also the anion occupies CCP lattice, whereas the cation Zn2 plus is placed in ATV. ATV. What do we mean by the term ATV? It's alternate tetrahedral void. So cation is placed in the alternate tetrahedral void, whereas anions are placed in CCP. Am I clear? What's Z effective for S2 minus? How much? CCP. Z effective 4. What's Z effective of Zn2 plus? Student, in a CCP lattice there are 8 tetrahedral void. If I talk about alternate tetrahedral voids, how many ATV? 4. Right? So effective number of zinc plus ion 4, effective number of S2 minus ion 4. So in one unit cell we have 4 Zn2 plus 4 sulfide ions. Right, students? Okay, one more thing. This one is my sulfide ion, and this one is your Zn plus 2 ion. And when I say R of sulfide ion plus R of Zn plus 2 ions is equals to root 3a by 4. One more thing, student, since this Zn plus 2 is placed in the tetrahedral void and size of tetrahedral void is 0.225 times the size of atom, so can I say R of Zn2 plus upon R of S2 minus is going to be 0.225. One most important point, coordination number, where this zinc plus 2 is placed in tetrahedral void, and if zinc plus 2 is placed in tetrahedral void, it will be surrounded by 4 anions. So coordination number of Zn plus 2, 4. Coordination number of sulfide ions is also 4. Student, if Z effective ratio is 1:1, coordination number of both cation and anion will be same. Am I clear? So if coordination number of cation is 4, the coordination number of anion has to be 4 only. Is this clear? Let's move ahead. The next type of AB type of a structure is Cesium halide structure, CSCl structure. Students, if we look at this particular structure, Cl minus, the anion is placed in every corner of the cube. Cl minus, 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 and Cl minus. So its effective number of Cl minus. Effective number of Z effective of Cl minus is 8 into 1 by 8. Cl minus is placed at every corner. Whereas if I talk about Cesium plus, Cs plus, it's exactly placed at the body center. Body center. This is the position of Cs plus. Am I clear? So basically, students, here the cation is placed in a cubical void. Cubical void. Am I clear? R of Cs plus upon R of Cl minus is equals to 0.732. One more important point, students. If I talk about the coordination number of Cs plus, basically it is surrounded by 8 Cl minus. The cation is placed in a cubical void. So what's the coordination number? 8. And what's the radius? What's Z effective ratio? 1:1. So if Z effective ratio is 1:1, coordination number has to be same. Coordination number of Cs plus is cation is 8. So coordination number of anion has to be 8 only. Am I clear? Students, moving ahead, the next type of a structure that we have to study is fluorite structure. I say it as AB2 types. AB2 types. Okay. Fluorite CaF2. Cation Ca2 plus, anion F minus. Student, here this cation, size of cation is somewhat larger as compared to the size of anion. Now, this cation is placed in CCP lattice. CCP, anion is placed in all tetrahedral voids. If it's placed in tetrahedral voids, what's Z effective? Z effective for this F minus is 8. What's Z effective for this Ca2 plus? 4. So Ca plus 2 in one unit cell is 4. F minus is going to be 8. 1:2. That's why the formula is AB2. Ca4, F minus 8. Am I clear? Now let's focus on coordination number. F minus placed in tetrahedral void. If the ions is placed in tetrahedral void, it will be surrounded by 4 ions. Am I clear? So coordination number of F minus is 4. Now one important point. If Z effective ratio is not 1:1, in that case, coordination number ratio is the inverse of Z effective ratio. If Z effective ratio is X:Y, Z effective, then Cn ratio is going to be Y:X, right? So for this fluoride ion, the coordination number is 4. So what will be the coordination number for this calcium ion? 8, right? Because Z effective for this calcium was 4. and Z effective for this fluoride was 8. So Cn minus for this, or sorry, coordination number of for this Ca2 plus will be 8, and coordination number of F minus in fluoride structure will be 4. Am I clear? Let's move ahead. Anti-fluoride structure A2B type. Best example Li2O, Na2O. Student, here the cation Na plus is placed in tetrahedral void, whereas O2 minus oxide is placed in Fcc lattice. If it is placed in Fcc lattice, what's the Z effective? Z effective for this O2 minus is going to be how much? 8. Sorry, 4. What's the Z effective for this Na plus? It's 8, right? Now, Na plus is placed in tetrahedral void. So, can I say it is surrounded by 4 O2 minus, right? This O2 minus will be surrounded by how many Na plus? It will be surrounded by 8 Na plus. So, coordination number of O2 minus is 8 and coordination number of Na plus. In case of anti-fluoride structure, the coordination number of cation is 4, whereas the coordination number of anion is 8, right? Brief discussion regarding the different types of ionic crystal AB, AB2 and A2B. Student, although we have some more type of ionic crystal, that's corundum structure, then we have that is Al2O3 structure, spinel structure, inverse spinel structure, but these things are not that important and they will give you the positions of ions there. You simply need to write the formula, so you don't need to remember the positions of ions there. Am I clear? Let's move ahead. Student, now let's discuss some questions related to this particular concept. The question is, a solid crystal AB has NaCl structure, that's rock salt structure. If the radius of anion is 200 picometer and the radius of cation will be, very simple one. Student, basically Na plus is placed in octahedral voids, right? Cl minus occupies Fcc lattice, right? We have studied the size of OV is equals to 0.414 times size of atom, right? And Cl 0.414 times the size of Cl minus. So size of Na plus will be equals to 0.414 into 200. 200 into 0.4 close to 80, 82.8 picometer. Am I clear, students? Let's move ahead. Students, moving ahead, the next topic which we are going to discuss is there on the screen, and it's impurities in crystalline solids. We have studied none of the crystalline solid is perfectly crystalline. It is bound to have certain defects, right? Pure perfect crystalline solid can only be obtained at 0 Kelvin temperature, which is not feasible, right? So students, every crystalline solids is bound to have certain defects. It's time to discuss about the different types of defects which we may see in a crystalline solid. Student, if I talk about the different types of defects which we observe in the crystalline solids, it can be written like this. Defects. It's classified first into point defect, line defect. This line defect is rarely observed. Mainly we observe defects at certain lattice points. So the major defect is mainly of points defect. Student, if I classify this point defect, it is further classified in 3 different categories: stoichiometric defect, non-stoichiometric defect, and impurities defect. Point defect is divided in 3 categories: stoichiometry, non-stoichiometric defect, and impurities defect. We'll discuss about all these defects briefly, don't worry. First, let's focus on this stoichiometric defect. It's further classified in 4 different categories, that is interstitial defects, vacancy defect, Schottky defect, and Frankel defect. So we have 4 different types of stoichiometric defect. If I talk about non-stoichiometric defects, it's of two types: metal excess defect and metal deficiency defect. How we can have excess of metal? Just by removal of anions or by addition of some extra metals. So metal excess defect is further classified due to anionic vacancy or due to addition of some extra cations. Am I clear, student? And the other one is metal deficiency defect. So it's time to discuss all these defects briefly. Let's move ahead. Point defect. Student, already discussed this point effect is mainly observed at certain lattice point. It is visible in a crystalline solids. Some effect is generated at one of the lattice sites. So in that particular case, student, we are going to have point defects. And point defects is mainly of three types. First, stoichiometric defect. Second one, non-stoichiometric defect. And third one, impurity added defect. Okay. Student, let's first of all talk about the stoichiometric defect. First of all, it's a point defect. Stoichiometric defect. In such defect, the stoichiometry of the molecule, the stoichiometry of the chemical composition, the stoichiometric ratio does not get disturbed. Am I clear? In such type of point defects, the stoichiometry of the molecule of the crystalline solid is not disturbed. It does not disturb the stoichiometry of the solids. They are also referred as intrinsic or thermodynamic defects. Basically, these are of two types: vacancy defects and interstitial defects. Although I have told you four types. Students, moving ahead, the next type of a stoichiometric defect which we have to study is interstitial defect. In case of interstitial defect, what happens? Some of the constituent particle, that is atom, ions or molecule, occupy the interstitial void. They get trapped in the interstitial voids of the lattice. Am I clear? And if some of the constituent particles will get added and it will occupy the interstitial void, can I say the mass of unit cell will increase? Cell will increase. The volume remains same. So can I say in case of interstitial defect, the density of the solid is bound to increase. Students, now one important point. Basically, in case of ionic solid, electrical neutrality has to be maintained. So in case of ionic solids, rather than defining this vacancy defect and interstitial defect, we define two other types of stoichiometric defect, and that is Schottky defects and Frankel defects. So basically, if I talk about ionic solids, they show Schottky defects and Frankel defects rather than showing this, or rather than saying vacancy defects or interstitial defects. For ionic solids, we name Schottky defects and Frankel defects as stoichiometric defects. Let's have a discussion about that. Frankel defect. It's somewhat related to interstitial defect. Student, what happens in the Frankel defect? Mainly shown by the ionic solids, perfect. The smaller ions, usually cation, leave their lattice sites and get trapped in the interstitial voids. Cation M+, it has left its lattice side and it's trapped in the interstitial voids. Am I clear? Still, if you see in this ionic solid, the number of cation is still equals to number of anions. So electrical neutrality is always maintained in case of ionic solid. So what happens in case of Frankel defect? The cation leaves its lattice points and gets trapped in the voids or gets trapped in the interstitial side. Am I clear? Okay. If I talk about the density, student, the mass remains unchanged. Cation has left the lattice side but is still there present in the unit cell. So mass remains unchanged, volume remains unchanged. So in case of Frankel defect, there is no change in density. Am I clear? There is no change in density of the solid. density of solid remains unchanged. Electrical neutrality is also maintained. Simply, cation is occupying, has left the lattice side and is trapped in the interstitial void. Shall we move ahead? Let's move ahead. It's also referred as dislocation defect. Why? Because of the dislocation of cation, M plus has left its lattice side, trapped in void, right? It does not change the density of the solid, already discussed. Friends, in general, this Frankel is defect is shown by the ionic solids, where there is large difference between the size of cations and the size of anions. The best examples are ZNS, silver halides, AgCl, AgBr, AgI. R of Ag plus upon R of I minus is too small. Am I clear? Basically, students, in case of Frankel defect, such type of defects make the solid a good conductor of electricity. Right? Let's move ahead. The next type of defect that we have to study is Schottky defect. What happens here? Student, here basically equal number of cations and equal number of anions are missing from the lattice side. If equal number of cations and anions will be missing from the lattice side, still the electrical neutrality will be maintained. Still the empirical formula will be maintained. Am I clear? Suppose initially there are 6m plus and 6x minus. Now, if it's Schottky defect, equal number of cation and equal number of anion should be missing from the lattice side. So if 2 cations are missing, 2 anions has not to be there in the lattice side. Am I clear? Okay. You can see from the diagram itself. This is my perfect ideal crystal, and if I talk here, one of my cation M plus is missing from here and one of the anion X minus is missing from here. So equal number of cations and equal number of anions are missing from the crystalline solid. Such defects are referred as Schottky defects. Still here, electrical neutrality is maintained. What about mass? The mass of unit cell decreases, and because of that, density will also decrease. Mass of unit cell decreases, and because of that, density will decrease, right? So in Schottky defect, density decreases, electrical neutrality is maintained. Decreases the density, right? Number of such defects in ionic solid is quite significant. For example, in NaCl, there are approximately 106 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube, there are about 10 raised to the power 22 ions. Thus, there is one Schottky effect per 10 raised to the power 16 ions. Although these data are not that important. Schottky effect is shown by ionic substance in which the cation and anions are almost similar size, right? R plus upon R minus ratio is almost close to 1. Basically, in case of Schottky defects, or Schottky defects are shown by the ionic solids where the cationic size and anionic size are similar, right? NaCl, KCl, CSCl, these types of ionic solid, so Schottky defect, right? Let's move ahead. Students, so till yet mainly we had discussed about the stoichiometric defect. Now let's start our discussion on non-stoichiometric defect. In case of non-stoichiometric defect, the empirical formula is not the same. The stoichiometry of the molecule gets disturbed. Either we may have excess of cations or we may have excess of anions. Am I clear? Let's have a look at the slide. The defects discussed so far do not disturb the stoichiometry of the crystalline solids. In case of stoichiometric effect, the stoichiometry is not disturbed. However, a large number of stoichiometric inorganic solids are known which contain the constituent elements in non-stoichiometric ratio due to defects in their crystalline structure. Basically, it's of two type: metal excess defect. Already I told you, either the cationic number will be more or the anionic number will be more. So either we have excess of metal or we have deficiency of metals. So if I talk about non-stoichiometric defects, we have two types: metal excess and metal deficient. Let's discuss it one by one. Now let's discuss the first type of non-stoichiometric defect, and it's metal excess defects. Now this metal excess defects can be of two types, or it can be formed from two types, either by anionic vacancy or by the addition of extra cations. Let's discuss the first case, metal excess due to anionic vacancies. Basically, students, it's mainly observed in NaCl and KCl type of a structure. When this NaCl structure is heated in the atmosphere of sodium vapor, the sodium atoms are deposited on the surface of the crystal. When I'm having a rock salt structure, and when this rock salt structure is heated over sodium vapor, this sodium vapor will ionize as Na plus electron. Now Cl minus from the lattice will diffuse to the surface of the crystal and will combine with Na plus to form NaCl, right? Now this Cl minus is missing from the lattice, and students, in case of ionic solids, the electrical neutrality has to be maintained. So this Cl minus will be replaced by electrons getting released from sodium vapor. Student, now in this ionic solid, we have excess of M plus, lesser number of X minus, although electrical neutrality is still maintained. Students, now this particular site which is where this X minus is replaced by electron, such sites are referred as F center, or we call it as far B center. Am I clear? Students, such type of defects imparts coloration property. Why? Because of the presence of these electrons. These electrons are unpaired electron, which gives paramagnetic behavior, and because of paramagnetic behavior, it imparts coloration. Am I clear? F center, simple, this X minus is replaced by electrons. So this particular site will be referred as F center or far B center. Okay. Friends, moving ahead, the next type of non-stoichiometric defect we have to study is metal excess defect, and metal excess defect due to extra cations. Student, what happens in such cases? Some of the extra cations get trapped in the interstitial voids, and because of that, the net number of cations will increase. The best example is heating of zinc oxide. Whenever this zinc oxide is heated, white color changes to yellow color, right? There is excess of zinc in the crystal, and now its formula becomes Zn1 plus Xo. The excess of Zn2 plus ion moves into the interstitial sites. In order to maintain electrical neutrality, the electron occupy the anionic sites. Am I clear? Let's move ahead. The next type of non-stoichiometric defect that we have to study is metal deficiency defects. Here, metal cations or cations are lesser in number as compared to anions. Basically, such type of defects are shown by the ionic solids where the cation is having variable valency. Let's try to understand it. Students, I am having a perfect crystalline lattice of FeO. This here FeO cation is there in +2 oxidation state, anion O2 minus oxidation state. Now what happens? I have removed 3Fe plus 2. 3Fe plus 2, right? 3Fe plus 2. So basically I have removed 3 cations. Now I have replaced these cations by 2Fe plus 3. Initially there was a shortage of 6 positive charge unit. I have provided that by adding 2Fe plus 3. Still one of the cationic site is vacant, but electrical neutrality is maintained. So can I say here in such type of defect there is deficiency of metal cations, or there's deficiency of metal atoms, right? Such type of defects are only shown by the metals having variable valency. A higher valency metallic cation replaces a lower valence. Am I clear? Let's move ahead. The next one is impurity defect. Here basically we do doping. Let's try to understand. I'm having a crystalline lattice of NaCl. It's an ideal crystalline lattice, right? Na plus Cl minus, equal number of Na plus and equal number of Cl minus. Students, now I'm going to do doping. I'm going to add some extra foreign material. Okay. What I'm going to do, I'm going to remove 2 Na plus. I have removed 2 Na plus. So can I say now this crystalline lattice will have a shortage of 2 positive charge unit? Now what I am going to do, I am going to replace it by Sr plus 2. Is the electrical neutrality maintained? Initially it was having a deficiency of 2 plus units because I have removed 2 Na plus. Now it's this 2 Na plus is replaced by 1 Sr plus 2. Can I say still here one of the cationic vacancy will be there? Am I clear, students? So can I say 1 Sr plus 2 in this impurity defect will cause 1 cationic vacancy. So if I am having 1 mole of SrCl2 added, how many moles of cationic vacancy it will create? 1 mole of cationic vacancy. Am I clear, students? Let's have a look at the slide. If molten NaCl contains little amount of SrCl2 is crystallized, some of the lattice sites of Na plus are occupied by Sr plus 2. Each Sr plus 2 replaces 2 ions. I have removed 2 Na plus, I have added 1 Sr plus 2, still there is 1 cationic vacancy. It occupies the site of 1 ion and the other site remains vacant. The cationic vacancy thus produced are equal in number to that of Sr plus 2. Am I clear, students? So students, this is all about the types of defects that we have to study in case of solids or in case of crystalline solids. So that's all, students, for today's class. I hope you enjoyed this particular class. If you have any doubt, please do mention in the comment box. I thank you all for watching this lecture.